Hello.
Good morning, Professor Alexandros.
Hello, do you hear me?
Yes, sir. Good morning, sir. Good morning, Dr. Dat Thanh. Sir, are you able to hear me, sir?
Dat, can you hear us?
Good morning, Dr.Naresh, sir.
Good morning. Hello, Professor Alexandros.
Hello,
How are you?
I'm good. How about you?
I'm fine too. What is the time there?
It's 10:30.
10:30 a.m. p.m.
Before noon, so it's okay.
Before noon, morning. Okay.
Yes.
Morning it rained heavily here. How is the weather there?
Here, you mean?
How is the weather?
It's
If you are
cloudy. It's cloudy.
Cloudy.
Yes. Yeah, so here it started, the autumn started. So soon we will have strong rains and temperature will drop.
Okay. So colleges are closed or?
No. We give lectures mostly online.
Okay, good.
There, what's the situation?
Here also slowly things have started back again, but still colleges and students are offline. I mean, they are online, not on regular classes are not fully started. Okay. So you generally work in ANNs, your specialization is?
I'm leading a group on machine learning and computational intelligence. So we work on statistical machine learning, deep learning, and applications in computer vision, time series analysis.
Very good. How did you come about this GOP? It was.
I don't know. So that played a big role in this work. So that will describe also all the small details in the session that will follow.
Okay.
So that is the big guy in this research.
Oh, so. Good. I have got you a mail. Thanks for sending the information. I'm going to submit tomorrow. I will submit it. Hopefully, we will start working. We will have meetings and all. And we'll work towards that.
Yes.
So you have a society there, CIS society and other societies are active in your college?
Not of what I know. No, I don't think. I'm a senior member of Signal Processing Society. So the Computational Intelligence Society, I don't think it's very active here.
Okay. Dat also has joined, I think. Hi, Dat. Can you switch on the video so that we can see?
Hello. Hello.
Hello, Dat.
Yeah. So can you hear me clearly?
Yeah, I'm able to hear you.
Okay.
Do you have
your video?
Do you want to switch on the camera?
I don't think I can switch on the camera. It said that I cannot start the video because the host has stopped it.
Okay, okay, okay. Shweta can.
Now you can do it. Now you can start your video, sir.
Okay.
Hi, Dat.
I
Oh. So you are in the hostel or you are outside? You stay where?
I'm in my place.
Oh, okay, okay, okay.
Yeah.
So,
Yeah. In Finland, we still work. We are advised to work from home, but we also have the possibility to work in a university.
Okay.
Yes.
So labs will be open during this period, or?
Yeah, it was closed 2 months ago, but at the moment it's open for researchers. But the teaching, most of them are still online. Yes.
Okay. How is the situation there? COVID-related situation, is it better now?
In Finland, it's increasing for the last few days, so I think people are a bit worried. Yeah.
Okay, okay.
So actually, it is worse than ever.
Oh.
Yes, the first wave was not so strong here. Okay. Now the second wave of the virus seems to be more. We have more cases.
Okay. So extra care should be taken, I think. Better to avoid moving out or something like that. Some advisories are there from the government.
So the government says that we should be careful if we use a bus. Any transportation means we need to wear masks.
Okay.
In the offices, we have instructions to have at most 2 persons in the office, and distances between us should be more than a meter always, something like this.
Okay. So hope we will overcome this very quickly. Yes. Otherwise, this online thing is good, but sometimes, physical meetings are more interactive.
Yes.
Okay, shall we start the meeting? Shweta, will you take over now?
Okay, sir. Good morning, one and all. This is Shweta Pesaru. Today we have 2 resource persons, Alexandros Iosifidis and Dat Thanh Tran. Let me introduce you Alexandros. Professor Alexandros Iosifidis is an associate professor at Aarhus University, Denmark. He leads the Machine Learning and Computational Intelligence group at the section of Electrical and Computer Engineering in the Department of Engineering. He received his PhD in 2014 from the Department of Informatics at Aristotle University of Thessaloniki, Greece. He has held postdoctoral research positions at Tampere University of Technology, Finland, and Aristotle University of Thessaloniki, Greece. He received his prestigious awards, including the Academy of Finland Postdoc Fellowship and the H.T. Orsted Forsker Prize for Research Excellence at a young age. He is a senior member of IEEE and he served as an officer at the Finnish IEEE Signal Processing Circuits and Systems chapter from 2016 to 2018. As of 2020, he serves as a member of the Technical Area Committee on Visual Information Processing of Eurasip. He is also currently serving as an area editor of the Signal Processing Image Communication Journal and associate editor for the Neurocomputing, IEEE Access, BMC Bioinformatics and PLOS 1 journals. He contributed in the organization of several international conferences as an area or technical committee chair, including IEEE ICIP 2018-19-20, EU SIPCO 2019 and IEEE ICA SSP 2019. So, and we have other resource person, Dat Thanh Tran. He is also from Tampere University of Technology. So we welcome you, sir, and you can start your session, sir.
Thank you for
Yes, sir.
Can you hear me?
Yes, sir.
Thank you for the introduction. As it was mentioned, I will give you a presentation of our generalized operational perceptron neural networks. And I will start with introduction on the methodologies and the description of the processes that we follow for training these neural networks. And later that will give you a hands-on session where he will introduce you the PyGOP library. This is a library where we have implemented our methodologies so that researchers worldwide can download it, play with it using their datasets, and also build their own research. So you will see that the library welcomes new submissions and new extensions of the methodology. So in our view, it is very nice if you can go through it with that in the next session, and then try to experiment with it, see the advantages that you can have by optimizing the neural network topology in terms of both the structure and also the type of transformations that each neuron can perform. So, as I said, I will give you a presentation of the generalized operational perceptrons methodologies. This work was conducted with Dat, who is now in Tampere University in Finland, with Serkan Kiranias, who is a professor in Qatar University, and with Mosaf Kabus, who is also in Tampere University. So, as all of us know, deep learning architectures are architectures which are formed by multiple hierarchical transformations of the input data, and the parameters of these neural networks are jointly optimized to achieve a goal expressed in the form of an optimization function, which is defined on the training data which are given to us, and the targets that we can create by using the annotations given by experts. During the last 10 years, they have achieved impressive performance levels in a wide range of applications. However, in order to apply these neural networks in our learning problems, we need to make many decisions. We need, first of all, to decide how the data needs to be preprocessed. We know that if the data is not preprocessed before introducing them in the neural networks, then the scale of the data might cause some problems in the outputs of the first layer. For example, if we use a sigmoid activation function and the magnitude of the vectors that we introduce to the network is high, then the weights of the first layer need to be very small in magnitude. This means that small changes in the weights of the first layer will introduce huge differences in the outputs of the first layer, and this is something bad for learning. We also need to optimize the topology of the network. This means that we need to define how many layers we need to use for the network and how many neurons per layer we should use. We also need to define what type of neurons we will use. Usually the neural networks that we used until now, before the generalized operational perceptrons were proposed, they were formed by homogeneous layers. This means that all the neurons in all the layers are formed by the same, are equipped with the same choices for the transformation. For example, we usually use summation. So in the neuron receives the outputs of all the neurons in the previous layer. It applies a weighted average, and the weights of this average value are determined by the weights of the neuron. And then we use one activation function for all the neurons in the network, except the last layer. For this layer, we usually use a linear activation function, or we use softmax activation function, depending on the problem that we want to solve. If we want to solve a classification problem, the softmax activation function is the default choice. If we want to use to solve a regression problem, then the linear activation function is the default choice. After defining what is the topology of the neural network, which type of neurons we will use and how we will preprocess the data, we need to define which of the optimization and regularization strategies we will use. In the last 5-6 years, many methods have been proposed which can speed up the training process of neural networks by dealing on how we can weight and how we can normalize the gradients which are obtained by measuring the error of the neural network in the output. While some design patterns became standard in the last years for specific problems, it is not necessarily true that for a new problem, if we want to solve a new problem, the same neural network types should be used. Here we can see some milestones for deep learning in the last years. We can see that the beginning of this explosion of using neural networks in scientific research came in 2012 when the AlexNet was trained on the imaging dataset and it improved the performance considerably. And then we can see that several other topologies of neural networks have been proposed over the years, and each of these topologies improve the performance for a small fraction of the error. So we can see that it took us to several years in order to come up with good neural network topologies to solve one particular problem. So this generates the need of creating meta-algorithms which can automatically design the topology of a neural network given a data set and annotations which can describe the problem at hand. So the idea of optimizing the topology of a neural network is not new. This approach was used in 1990s, where researchers were using evolutionary algorithm methods in order to optimize both the weights of a neural network and the topology of the neural network. However, because in order to optimize different topologies of neural networks, we need to train the networks. This approach was not able to give us good results for big problems and big datasets, and it was restricted only on more or less toy problems, toy datasets. In 2012, a method by Stanley et al., which was called NEAT, proposed a mechanism to perform a crossover which was able to capture the information from both parents in the evolutionary update, and this gave a boost in these evolutionary algorithms for optimizing neural network architectures. In the last few years, the method which was proposed and reinitiated the interest of researchers in optimizing neural network architectures is called neural architecture search. And this method was able to show good performance on big data sets. And this is why now this research topic is active and people try to optimize automatically the topology of neural networks. However, here we should note that most of the neural architecture search methods are extremely computationally intensive because they need to train some thousands of neural networks in order to select the best topology for the problem at hand. For example, the NAS method was run using 800 GPUs in parallel, and if I remember correctly, they tested 12,000 network topologies in order to select the best one. So many works which followed this initial NAS method adopt a more structural architecture search space. So this means that they don't try to find any possible combination of layers and neurons per layer in order to find the best solution. But they use common design motifs, so they use specific types of layers which are combined in specific ways. And this gradually saturated the performance that can be achieved. However, these methods now, by reducing the search space, were able to give decent performance in big data sets without requiring a huge computational power. So with the generalized operational perceptrons, we push in a different direction. So our idea is that it might be the case that we don't need to find the best topology for a network, which is very complex topology, but we might need to define different types of transformations on different layers in order to find the patterns needed to solve the problem that we want to solve. So with generalized operational perceptrons, we push for greater exploitation with the same number of parameters compared to increasing the parameters in order to define topologies which can reveal patterns of interest in our problem. So here we can see how the generalized operational perceptron neuron compares with the standard perceptron neuron. So the traditional neuron model, the perceptron neuron, performs an affine transformation. So each neuron receives as input all the outputs of all the neurons in the previous layer and applies a linear transformation. And after this real value is obtained for each neuron, then we apply a nonlinear element-wise activation function. For example, ReLU, sigmoid, tanh, and so on. It was shown that biological learning systems don't follow exactly this approach. So in biological learning systems, different types of neurons are placed in different positions of the biological neural network, and they perform specific transformations of the input signal in order to efficiently process the information that they receive. For example, in the mammalian retina biological neuron system, approximately 55 different types of neurons are used, and they guarantee the efficient transformation of the visual information to the brain. So here you can see a biological neuron. So the information from the neurons which are connected to this neuron is received from the dendrites. The dendrites, the information from the dendrites then is transferred to the soma, and the information of the different neurons is combined. And then the combined information is transferred to the terminal buttons through the axon. And in the terminal buttons, you can see here that we have the synaptic gap. The synaptic gap is responsible for the nonlinearity that we observe in the transmission of the signals in the biological neurons. So if the information which is received in the terminal button of this neuron is strong enough to break the synaptic gap, then the information is passed to the dendrite of the next neuron. If the information is not, if the signal is not very strong, then this neuron doesn't fire and the information does not pass to the neuron in the next level. So the generalized operational perceptron was proposed to mirror these operations of the biological neuron. So we modeled the this transmission of the information from one neuron to the other by using 3 operation types: the nodal operator, the pooling operator, and the activation function. So the nodal operator determines which type of transformation that we will perform on the neuron under consideration. The pooling operator determines from which neurons the current neuron will receive information, and the activation performs different types of nonlinearities. The term operator set refers to one specific combination of a nodal, a pooling, and activation operators. And by combining different choices for these 3 operators, then we can achieve transformations which are highly complex for each generalized operational perceptron neuron. These choices can be stored in operators library. So here you can see that we can use for nodal operators multiplication, exponential, harmonic, quadratic, Gaussian, and different of Gaussian operators. For pooling operators, we can use the summation, 1 decorrelation, 2 decorrelation, and maximum. And for the activation function, we can use sigmoid, tanh, ReLU, and any other activation function that is used in standard neural networks. So the biggest importance for adding a new operator in this library is that we can define the gradient of this operator with respect to the signal. If this operator is differentiable, then we can extend the different types of operators here by adding new operators and follow the same process for training as we will describe next. Here we should also note that the perceptron neuron can be obtained by using multiplication, summation, and sigmoid activation functions. So we see that the standard multi-layer perceptron networks are specific realizations of the generalized operational perceptron networks. Now, optimizing the networks formed by generalized operational perceptrons involves solving 2 tasks. First of all, we need to define what is the operator set for each neuron forming the neural network. And then we need to calculate the parameters of each neuron. So this means that similar to the NAS methods, we can define the topology of the network. However, since selecting different operator sets for each neuron might affect the topology of the network the optimal topology for the network that we need to select, solving these 2 problems at once is highly complex. In order to deal with this issue, we proposed a number of training methods. The first one is called progressive operational perceptron. So in this method, we need to define the maximum number of layers for the network, and we need to give a template for each of the layers. So we need to define how many neurons we will use on each layer. And we make the assumption that on each layer we should use the same type of neurons. So this means that the progressive operational perceptron training method can generate layer-wise homogeneous networks. However, the entire network is heterogeneous because the type of neurons on different layers can be different. So, yes. So let's say that we have trained one layer of the progressive operational perceptron network. Then we fix the parameters of the network so far, and then we need to add one more hidden layer. So the POP method optimizes the kth hidden layer and the new output layer, including the operator set assignment for the new hidden layer and the output layer, and the synaptic weights. So we start in the first step, we start by using the input, and we plug an output layer, and we optimize for the first layer. Now, because the operator sets that are used for the hidden layer and the output layer affect the performance of the network, and also affect what should be the best operator set for the other layer. So the best operator set for the hidden layer affects what should be the best operator set for the output layer, and vice versa. We proposed the two-pass grid iterative sets algorithm, which can find an optimized set of operators for the hidden and the output layer. So the first pass of the grid iterative sets algorithm sets a random assignment for the hidden layer K. So this means that we have the library of the operator sets which are available for our network to choose, and then we select an operator set for the neurons of the kth layer. Then, given the assignment in the kth layer, for each operator set in the library, we assign to the output layer this operator set. So this means that now this is fixed, and now we need to define what type of neurons we should use for the output layer. We update the weights in the layer K and the output layer. So this means that we train for few iterations, for few pokes, the weights of this layer and the weights of the output layer. And then we record the mean-square error achieved by this network. We follow this process now for all the type of operators for the output layer, and then we have a vector with the mean-square errors for the different types of operators for the output layer. And we select the operator set with the lowest mean-square error for the output layer. Now, given that the operator set for the output layer is optimized, so we know, for example, that for the output layer we should use summation, we should use one decorrelation, and we should also use sigmoid. Then the question is, what is the best operator set for the hidden layer? So now we keep the operator set which was selected for that layer fixed, and we test all the operator sets for the hidden layer. So this means that we train multiple networks, each of which have a different operator set for the neurons of the hidden layer. And we record the performance of each of the networks. So again, now we have a vector with the mean-square error values obtained by using different operator sets for the hidden layer. Now, since this operator set is fixed now, we have selected the best operator set, the question arises, is the output, the operator set used for the neurons in the output layer the optimal one? So in order to find this out, we again now fix the operator set for the hidden layer, and then we try to find the best operator set for the neurons of the output layer. We follow the same process, so we train networks using the output different operator sets. We record the mean-square error, and then we keep the operator set which provides the minimum error. We follow the same process for the hidden layer once more, and we select the best operator set, and that's it. So after this process, so after applying 2 steps of optimizing the operator set for the output layer and for the hidden layer, we converged to a solution which defines which are the best operator sets for the two layers. Now, as you may imagine, this process is computationally intensive because we need to train multiple networks 4 times. We need to follow 4 times the same process, and each process needs to train multiple networks. The number of networks that we need to train is equal to the number of operator sets that we have in our library. So afterwards, we've proposed a faster progressive operational perceptron method, which we called POP-fast. And the idea is that if we can reduce the number of networks that we should optimize in order to select the operator sets for each of the layers, then this would lead to much more efficient training processes and hopefully to similar performance compared to the original POP method, and better performance compared to the standard MLP networks. So in the POP-fast method, we made an assumption which says that the output layer doesn't need to have, we don't need to select an operator set for the output layer. We can fix the operator set for that layer to be linear transformation, so summation, pulling from all the neurons of the previous layer, and then linear activation function, or softmax if we want to optimize a network for classification. By making this assumption, now we need to optimize only a much lower number of networks because we need to find only the operator set for the hidden layer. Okay, and someone would ask, okay, but now we don't optimize the operator set for the output layer. Isn't this a suboptimal solution compared to the POP method? Our explanation, we will see later that the POP-fast method usually give the same performance or even better in some cases compared to the POP method. And our explanation is that by fixing the operator set of the output layer to summation, so linear transformation, and sigmoid or softmax activation function, in essence, we have exactly the same information as by optimizing the operator set for the output layer, but we need to have one more hidden layer optimized for our topology. So in practice, we highly reduce the number of networks that we need to optimize in order to find which is the best topology for our network, and we might need to have a network which has one more layer compared to the POP method. Now, the POP method was proposed and was published in the neurocomputing paper Progressive Operational Perceptrons in 2017, and the POP-fast method was proposed in our paper in neurocomputing 2020, which is called Progressive Operational Perceptron with Memory. Now, let's see, and here is a process for training this network. So, as we said before, the output, the operator set for the output layer is fixed. It's summation, it's a summation and pulling from all the neurons in the previous layer plus linear activation function or softmax, and we need to optimize the parameters of the network and to find which is the best operator set for the hidden layer. So we train we train n single hidden layer neural networks, where n is the number of operator sets which are listed in our library. And then we record the mean-square error for all these single hidden layer networks, and we keep the network with the best mean-square error. Also, for the POP-fast method, we don't use an absolute error for stopping the progression of the neural network, but we use a relative error compared to the performance that we achieve using a neural network with one fewer number of layers. Now, the POP with memory method tries to exploit also information that was obtained in the previous layers of the neural network. So let's see, for example, this network here. So we see that after we have trained this and defined this layer, the green layer here does not receive directly information from the red layer. However, it receives information after the transformation performed through the yellow layer. Okay, so the POP memory method tries to exploit information for this layer coming from the previous layer and layers before the previous layer. So we want to formulate an objective function for the network growth, which at each layer learns a new hidden layer that complements the formation of the previous layers. And this means that we want to create deeper layers which can synthesize new features and also can encapsulate features which have been learned in the previous layers. So in order to achieve this, we tried two approaches. The first one is to use PCA of the representation of the feature space obtained in the previous layers, or LDA on the same feature space. By using PCA, we try to preserve the information of the feature space obtained in the previous layers. By using the LDA approach, we try to keep the discriminative information of the data representations in the feature spaces of the previous layers. So here we can see how we can incorporate the memory path in our POP network. So before we had the input, we had the hidden layer which we want to optimize, and we had the output layer which we also want to optimize. Now we also add a memory path. So we use the data representations in the input layer, we apply the transformation, the linear transformation, and then we form the sub-layer G1. And this G1 is now fixed because this transformation from the input to G1 is trained by using LDA or PCA. And now we want to train the F1 path, the F1 sublayer, such that the output will give good performance. So this means that the sublayer F1 is optimized such that it will complement the information that we have in G1, which is the information of the input. Okay. So after we create the first layer, now we fix everything here. So we fix the operator set assignment for F1. We fix the weights from input to F1, the weights from input to G1. And now we want to follow the same process once more. So this means that we combine the F1 and G1. Now this is the feature space determined by the first layer of our neural network. And we apply PCA or LDA using the data representations in this feature space. This projection determines the weights mapping this combined representation to G2. And now, given that we have G2, we want to find the best F2 sublayer and output layer. So we optimize the weights from the first layer to F2 and from F2 combined with G2 to the output. So again now the F2 sublayer tries to find a complementary representation to the representation which is listed in the G2 sublayer. And remember that the representation in the G2 sublayer is a compressed version of the representation that we obtained for the combined F1 and G1. Okay, so we can see that the output layer receives information from both F2, but also from the first layer through G2. The same thing here. So the second layer receives information from F1, but also from the input through G1. So we can see that by using this memory path, the output layer receives information from all the previous layers directly. Okay, so remember that here we have linear transformation. So this is W2 times this vector. And now this part of this vector is W1 times this. So this here can be expressed as a linear combination of a linear transformation of this part, which is a linear transformation of this part, plus the non-linear transformations which are expressed in F1 and F2. And here you can see the schematic representation again of the training process. So again, for the POP memory method, we need to define the maximum topology for the network. So we need to define how many layers we need to use at most for our problem. And we need to give the number of neurons per layer so that we only optimize the type of transformation, so the operator set for each layer. So in the first iteration, we use the input. We create an output layer which is equipped with the targets of the training data. We apply the linear transformation of X of the input, and then we optimize for F1. In the second layer, we fix F1 and G1. We apply the linear transformation to obtain G2. We plug here the output layer which is equipped with the targets of the training data, and we optimize for F2. And we follow this until the relative improvement of the mean-square error at the output layer is very low. So this means that in practice, we don't gain anything by adding more layers. So if this happens, then we stop progressing the network. And in this example, you can see that in our initial guess, we said that we will have 4 hidden layers. However, after adding the second hidden layer, we decided to stop the training process. Now, in all the methods that we described before, the layers that we were learning from for the network were homogeneous. This means that all the neurons in one layer can apply exactly the same transformation. For example, they can apply an affine transformation plus an affine transformation of the entire layer of the vectors coming from the previous layer combined with a RLU activation function. The heterogeneous multilayer generalized operational perceptron method was proposed in order to create fully heterogeneous networks. This means that each neuron of the network can have can apply different transformation compared to any other neuron of the same network. So also the limitations of the previous methods is that they require a predefined template of the maximum topology. So the user needs to give to make a guess on what is the biggest network that we need in order to solve the problem. Also, they generate homogeneous layers for the network, and also they require a high computational cost because the operator set evaluation is performed by applying backpropagation. So in fact, we train multiple neural networks from scratch until convergence. The heterogeneous multilayer GOP method addresses these limitations by building each layer in a block-wise manner. So this means that the neurons on each block will be homogeneous. However, because each layer is formed by multiple blocks, the layer can be heterogeneous. The number of neurons per block is a parameter that is provided by the user. So in the extreme case, one block of GOPs can be formed by a single GOP, a single neuron. So this means that the resulting network will be fully heterogeneous. So we allow a different operator set for each neuron on each layer, and the evaluation of the different operator sets is done in a fast manner. So similar to the pop-fast method, the output layer is equipped with a linear activation and linear transformation. And we evaluate the operator set assignments for initially by using a randomized procedure. So let's see how this is done. Let's say that we have our input vectors and our target vectors, so the output layer. We form a block of generalized operational perceptron neurons, and now we create the input weights by sampling them from a random Gaussian distribution, and we solve the problem. So after mapping the input data to the hidden layer, then we train the output layer weights by using least squares optimization. So, and we do this process for all the operator sets that are listed in our library. After doing this, then we find what is the best operator set for this block, and now we add one new block. Again, the block here is fixed, and now we need to find what is the best block, what is the best operator set for this new block of neurons. We do this again by randomly initializing the hidden layer weights and solving for the output weights using least squares. We do this for a number of blocks, and at some point we find out that by adding one more block, we don't gain anything in performance. So this means that we don't need to add this block, and we can keep this layer by using only the blocks up to this block here. Now, after doing this, we create a new layer which has one block. Again, this part is fixed. We randomly initialize the weights for this layer, for this block, and then we map the representations of the data from this layer to this block, and then we solve for the output weights by applying least squares optimization. We do this for a number of blocks, and then again, at some point, we don't gain anything in performance if we add a new block. Now, until now we described how we build each block, each layer by using multiple blocks, and how we stop adding blocks on each layer. After determining how many blocks we should have on each layer and optimizing their parameters, we now need to also decide if we need to keep this layer or the performance that we achieved by using one layer less was adequate for achieving the goals of our problem. So in practice, what we do is that at step M, so after finding what is the best topology for this layer, we compare the performance that we achieved by including this layer on our neural network versus what is the performance that we achieved without this layer. If the performance that is achieved by using the smaller layer is competitive or even better than by using the bigger network, then we stop progressing the topology and we keep the neural network which has the smallest number of layers. If the performance that we obtain by including the new layer in the neural network is better than the performance without this layer, then we keep this layer and then we proceed in adding one more hidden layer, again building that layer in a blockwise manner. Okay, so here we describe how these steps are performed. So the random weights for each block are drawn from a uniform distribution, not a Gaussian distribution. A uniform distribution with ranges from -1 to 1. And then the output weights are optimized by solving this least squares problem, where Y is the matrix which contains the targets for our data. Okay, and then after obtaining these output weights, then we optimize the parameters of the new block for some epochs using backpropagation. So this heterogeneous multilayer generalized operational perceptron method was published in IEEE Transactions on Neural Networks and Learning Systems in 2020. And in this paper, we compared the performance of this training process with all the POP-based methods and with other progressively trained neural networks. Now, I will present you some of the experimental results that we obtained by using these methods. So in the beginning, I will present you results on several databases coming from computer vision problems for the POP fast, and POP memory methods. So here you can see some statistics of the datasets that we used. And we compared these three methods with the stacked extreme learning machine method, the broad learning system method, and the progressive learning network method. So we can see that the POP fast performs similar or better compared to the POP method, and it is much faster compared to the POP method. Also, we can see that by adding the memory path can improve performance. However, it also increases the computational cost for some seconds. And the computing methods, while being extremely fast, they cannot achieve comparable performance to the POP-based methods in these problems. And here we can see some results also in image classification datasets. So again, we can see that the POP memory methods achieve the best performance. We can see that POP memory with PCA is usually better than POP memory with LDA. And we can also see that the other methods, so the SELN, the BLS, and PLN method achieve inferior performance compared to the POP-based methods. Now for the heterogeneous generalized operational perceptron method, we used multiple datasets, and we can see the statistics of the datasets here. We compared the heterogeneous multilayer GOP method with the POP method, with the broad learning system method, with the progressive learning network, and the progressive MLP method, which the progressive MLP is the same as the heterogeneous GOP method. However, only the operator set that is used for each neuron is the same as the operator set used for multi-layer perceptron networks. So it is summation using all the neurons of the previous layer and then ReLU. Here we can see the performance accuracy, so classification performance for the different methods on these datasets. So we can see that the heterogeneous multi-layer generalized operational perceptron method achieves the best performance in all but 3 datasets, and the best performance in these datasets comes from the progressive MLP method. So this means that optimizing the topology of the neural network in a block-wise and layer-wise manner gives the best performance, because it can determine what is the best number of neurons on each layer. Here we can see now the number of parameters of each model. So we can see that even though our heterogeneous multi-layer GOP method achieved the best performance in most of the datasets, it also requires the smallest number of parameters. So this means that by using different operator sets for different neurons can lead to determining the transformations that are needed in order to determine the patterns which are important for solving the problem at hand, and it requires a smaller number of parameters in order to achieve good performance. Here we can see the histogram of the operators used in one of the experiments. So we can see that indeed multiplication, summation, and ReLU are the most commonly selected operators. However, we can see that also all the other operators except the soft plus operator have been selected in a considerable number of times. We applied these methods in various problems. One of them is the prediction of the mid-price election of stock market data. So here in this problem, we use the limit order book data, and we create features which aggregate information from a short-term window before the current time instance. This problem of the mid-price direction prediction is extremely unbalanced for the classes involved. The 3 classes that we used are mid-price stays stationary, mid-price goes up, and mid-price goes down. So the number of samples which form the stationary class is extremely higher than the number of samples which form the classes going up and going down. And in order to deal with this issue, we need to use a weighted least squares method for optimizing the output weights on each iteration of building new blocks for the heterogeneous multi-layer generalized operational perceptron method. Here we can see some results. So remember that this problem is imbalanced. So the best metric for measuring the performance of the methods is the F1 score. So it is the average F1 score over all the 3 binary classification problems. And we can see that the heterogeneous multi-layer GOP method achieves the best performance. Here we used also all the previous methods that I mentioned. And so the SCLM, BLS, PLN, we used the rich regression method, which is widely used for this problem. We used single hidden layer feed-forward networks, and now these methods here exploit the input data as back of features. So as they create a back of features representation. The neural back of features model is a model which was proposed by us for mid-price prediction problems, and optimizes the way to generate the histogram based on the multidimensional input time series. This is multi-way discriminant analysis. This is multi-way subset discriminant analysis. This is multi-way regression, and this is weighted multi-way regression. So these are tensor-based methods. We applied also this method on learning to rank problems. So we used two widely adopted datasets for learning to rank, for evaluating the performance of learning to rank methods, the MSR LR Web 10K, and we created a dataset from ImageNet, which can serve as an image retrieval problem. We used the normalized discounted cumulative gain and the mean average precision metrics to measure the performance of the tested methods. And again, we can see that the heterogeneous multilayer generalized operational perceptron method achieves the best performance compared to the previously mentioned methods, random forests and support vector machine. And again, we can see that the performance, also here we can see that the number of parameters that is needed for our method is small. So we can see here that the support vector machine requires an extremely small number of parameters. This is reasonable because the SVM method requires only one vector for classification. However, we can see that the random forest requires a huge number of parameters compared to the other methods. Another problem that we tested this method is the phase verification problem. The main idea here is that we can show that we can use transfer learning in order to exploit already trained neural networks, convolutional neural networks, which can extract image representations and then feed these image representations to the heterogeneous multilayer generalized operational perceptron for performing the classification task. So we applied the experiments on the CoLab Bay, label space in the wild, and the public figure datasets. And we used the representation length from the MobileNet network, the output of the 13th convolutional layer. We can see here performance. So the heterogeneous material generalized operational perceptron method outperformed the ELN, BLS, and PLN methodologies. And also we can see that the number of parameters is close to the number of parameters for the other networks. And here we can also see that measuring the performance by using the ROC curves also shows that the heterogeneous multilayer generalized operational perceptron method can build networks which can outperform the other methods in the retrieval, in the phase verification problem. Now, we made publicly available implementations of our codes, and we included them in the PyGOP library. This library is open access, and you can download it and include it in your Python implementations and use our methods which have been optimized in the way that was used in our experiments, and also they have shown that they are extremely competitive compared to other methodologies. That will give you an introduction to this library and how you can use it for training and evaluating networks for your datasets. That's it from my side. If you have any questions, I will be happy to answer.
A very interesting lecture, Professor Alexandros. Only one or two questions I have. Some places I'm seeing that the performances, when you compare with other methods, they're marginal, whereas you have said that the memory and the other parts, the number of parameters and other things are better. Yeah, I think somewhere RF, random forest, you said operating cost is higher, and
Yes.
operating cost and ImageNet is higher for RF, but lower for HEML COP.
Yes.
Now, now my question is like the computational complexity, if you take the choosing of these operators and such kind of other search, what is the kind of timeline that you are looking at? And what is the kind of dimensionality you said is around only 512 kind of a dimension you have taken in some places. So if it is higher dimensional data, like what will be the performance of this particular GOP?
Okay, so here we need to mention that these heterogeneous material GOPs and the POP-based methods receive as input vectors. We have also extended this line of work in for networks which can receive as input images. We call them operational neural networks, and they have shown that they can outperform CNNs in image denosing and image restoration problems. Now, in this case, for the GOPs, the input is a vector, always. The same holds also for the other, for example, let's take this example. So we can see that here we use CNN-based features. We have not observed any issue in using higher dimensional vectors as input, because these are neural networks which can receive any dimensional input data. I don't see any problem to use high dimensional data, but these methods cannot use structured data. Structured data are, for example, time series, or they are images.
Now, my point is there may be redundancies in the dimensions, right? So a lot of data related issues may be there. So higher dimension, though it is there, there may be fewer kind of dimensions that are really important. So that will be taken care of in the algorithm.
So you mean that if the method is able to find which are the most important dimensions of vectors?
Yeah,
yes. So actually, this can be achieved by selecting different types of operators. So the methods can reveal this type of information. Let me go back. So here you can see that in the operator set we have the pooling operator. And this pooling operator means that from which dimensions of the previous layer should we collect information and combine it. So the standard approach of the MLP assumes that you pull the information from the entire vector of the previous layer, so from all the neurons. And we make the assumption, and this assumption is true in practice, that the weights that are optimized for the task at hand will be able to weight higher the dimensions which are more important for the problem. So the main assumption also holds for the POP-based networks and the heterogeneous material generalized operational perceptron networks. So because we optimize the networks for achieving the best performance at the output, the parameters of the weights of the neurons will highlight the dimensions which are more important from the previous layer. I don't know if I answered your question.
This is a fully connected network?
Yes, this is a fully connected
network. Or any pruning
network.
is done? Like...
No, we don't do pruning, so it is a feed-forward network.
Okay.
And the POP memory is a fully connected layer network with skip connections, with memory paths.
Okay. Okay. Anybody can ask for questions?
Participants, if you have any questions, you can post it in the chat box.
Maybe I can also show you this here. Let me find it. Can you see this? Not the presentation, but the website.
Yeah, yeah.
Okay, so operational. Now, the methods that can take as input structured data like images are we call them operational neural networks. We also have a Python implementation of it. And so the idea is that we can get as input an image, and then we can regress to another image.
Okay.
And this type of problems, in this type of problems, we can find the image denoising problems, image transformation problems, and image synthesis. But optimizing this type of networks, the operational neural networks, is much more complex compared to the generalized operational perceptrons, because if we use for the GOP-based networks, we can use as output one target vector. For this here, for the CNN-like networks, it is difficult to have as output one vector and optimize layer-wise the network. Because in the first layers, usually the parameters of the network learn low-level features, like edges and lines and so on. Okay, that's it.
Another one is this input layer, this MSC you are computing, right? At each layer, at the end of, let us say, layer 2, and then another layer you are adding at that point. So yeah, somewhere at the end only you have the output. So this MSC, how are you computing at each end of the layer?
So the MSC is calculated at the output layer always, because
but you should have the output there, no? How do you calculate the MSC?
What do you mean? So we have the target vectors. If we have a classification problem or a regression problem, so we have the target vectors, we have the outputs of the network, and then we calculate the mean square error. So we have as input here many vectors. Okay. Each of the vectors is a sample, and then each of the vectors is equipped also with a label or a target vector. And then we have many target vectors for the output, and we have also the predicted output. And the predicted outputs are used with the target vectors to calculate the mean square error.
So your vector has both, the output also is there in the input, right? That you will compare at the output, what is predicted, right?
So we have the predicted output, and then we have the desired output, which is the target vector. And then we use the target vector, which is the desired output, with the predicted output, the mean square error between these vectors.
Okay, it's interesting. So we will discuss more on this. I think now we will have a small, as a token of appreciation, I think, Sweta, can you present a memento?
Yes, sir.
Professor Alexandros, thank you for your wonderful lecture on GOPs and the advances in the operational perceptron concept. Okay, it's a token of appreciation. We're showcasing this certificate. We will also mail you the certificate once the program is completed today. Thank you.
Thank you very much for the invitation, and it was my pleasure to be here and talk for our work.
Thank you. Sweta, now there is a break, or
Yes,
we are continuing with the next speaker, Dat?
There is a break, sir. At 3:30 we'll start the session, sir. Practical session.
Okay, we will come back at 3:30.
Yes, sir. Participants, please join back at 3:30. You can stay. Let's take a break for 15 minutes, 10 minutes.
Yes, so do you see my presentation now?
Yes, sir.
Okay, hello everyone, my name is Dat, and in these sessions I will present our open source Python library for generalized operational perceptron. The library is called PyGOP, and it's publicly available in Python repository. The content of my presentation is as follows. First, I will give an overview of PyGOP, which was developed by us to facilitate the development of GOP-related algorithm. Then I will go through the installation process. Then after setting up development environment, I will show you how we can quickly run existing algorithms in the libraries, the common interface of the package, the data feeding mechanism, and then we will go through some real code examples. And finally, I will go through some miscellaneous things such as the customization or how you can contribute to our package development. So for the overview of our library, we have the source code, which is hosted online in the following GitHub repository. So if you are in GitHub, can you see my repository now?
No, that I think you should share your screen, not the presentation.
Okay, let me try desktop too. Okay. How about it now?
Yes.
Yes. Okay. So this is the GitHub repository of our package, and here we have everything available in this repository. So if you are also a GitHub user, and if you find our library interesting, you can consider giving us a star here to improve the visibility of our package. Also from here, you can easily access the documentation. We also have the online documentations. If you click in this bag, it will lead to the documentation page. And in the documentation, we have very detailed information about every aspect of our libraries. And on the left-hand side, you can see all the information here about installations, about information changes in the package. And for the user guide, it gives you the main approach or all the required information, and you can start using it after the installations. And now the features of our libraries, we have many features. We target the library for many features. Firstly, it is reproducibility. So as you've seen from the previous presentations, we have existing algorithm that has been proposed for GOP-based networks, and all of them are now included in these libraries. So this allows researchers to easily benchmark our algorithms in their research work. Also, the second feature is the flexible computations. Our library can be run on both CPU or GPU with just one line of configuration. In addition, our library can also be used in a cluster environment which uses Slurm job scheduler. Due to the modular design, the development for different cluster environment is very straightforward. The third feature is the scalability. Besides the support for distributed computation environment, then we also have a very efficient data feeding mechanism that allows the user to load and pre-process the input data in mini batches. So if you have very large data, this allows you to handle the memory complexities very efficiently, especially for the large data set. The fourth feature of our library is customizations. So in our library, we have built-in operators or operator set, but you can also provide your own definition of the operators, that is, you can come up with novel operators, or if you have prior knowledge what kind of transformation that is suitable for your problem, then you can also define it using our library easily. In addition to the operators, we have metrics, we have loss functions that can be defined by the user also in a very suitable and easy manner. The final features of our library is reusability. So after training your model, you can save the model and load it later. Also, our library has the features that it automatically saves the checkpoints during computation, and when you restart the relaunch the script, it automatically resumes the last checkpoints when the script is run again. So this is to prevent long experiment being interrupted and having the intermediate results saved.
That we see only your first slide.
So you don't see this second slice? Do you see the changes to?
Okay, now we see the second slide.
Okay, it is in installation now, right?
Yes.
Yes, okay. So firstly, in order to work with our library, then you need to install and correctly set up the library on your local development. So installation, our library depends on two major packages, that is TensorFlow. That is required to be installed separately as the dependencies. So before installing our library, then you need to install TensorFlow. Here, I should also note that at the moment, our package is only supported for Unix-based operating system like Linux one. And for the TensorFlow installation, we only support TensorFlow version 1 at the moment. And for TensorFlow version 1, then we have two separate packages for CPU or for GPU. So if your machine or if you intend to use CPU, then you should only install the CPU version. And if you intend to use our package with GPU, then you should install the GPU version. For GPU TensorFlow, we recommend install TensorFlow 1.14.0, and the requirement for GPU version is that you should have QDNN, and we recommend that you should install QDNN 7.6.5 and CUDA Toolkit 10.0 as a dependency for TensorFlow GPU package. And here I list out the command that you can use to install the dependency for QDNN and CUDA Toolkit. Here I use CoLab Package Manager, and I also recommend you to use this Meta Package Manager to ensure that every dependencies are suitable. After installing QDNN and CUDA Toolkit, we can install TensorFlow GPU. And after installing TensorFlow GPU or CPU version, then we can simply install our PyGOP package using the pip command, pip install PyGOP. Now I will open a terminal and show you how I can actually do that on my local machine. So, do you see my terminal now?
Yes.
Yes.
Okay. So, first of all, I use Anaconda to manage the package, and I also advise you to create different development environment for different use case. So now, for example, I will create a development environment for PyGOP, and because my machine has some GPU, so I will create a development environment called PyGOP GPU. Also, I will use Python 3.7. Yes, after creating a new environment, then I will activate it. As you see here, it changed from the basic environment to the PyGOP environment GPU. After this, I need to install TensorFlow GPU, but remember that before installing TensorFlow GPU 1.14.0, I need to install QDNN 7.6.5 with this command. So I simply copy this command and paste it here. After that, I will install CUDA Toolkit with this command. And finally, installing TensorFlow GPU 1.14.0.
There is a request to move the screen a little bit on the upper side. They are not seeing your commands. That
Sorry?
they are not able to see your commands.
So,
The terminal, you can just move it. Yeah.
okay. Yes. So basically what I've just done is to create an environment and run 3 commands in sequence to install QDNN 7.6.5, then CUDA Toolkit 10.0, and then TensorFlow GPU 1.14.0. And after installing them, installing TensorFlow GPU, we can check it by running the command conda list to list the package, and also to check if any package named TensorFlow And here we see we have TensorFlow GPU 1.14.0 installed. After installing TensorFlow GPU, then we can simply install our package PyGOP by typing pip install PyGOP. So this will install all the other dependencies such as Keras, Dio, Joplib, etc. So that is for the installations. Now, after installing the package, then I can introduce you the main content of the library. At the moment, our library supports the following main algorithms. The first one is POP, which is Progressive Operational Perceptron. The second algorithm is the faster version of POP, which is called POP-fast. We also have Progressive Operational Perceptron algorithm with memories, which is called POP-mem. And finally, the heterogeneous version of GOP, which is HML-GOP. And here I should note that the green text, it's also the abbreviations, they are also used for the class name in the library. So you can use these abbreviations to create the class of a model. Here comes the interface of our libraries. We try to expose a common interface for all of the algorithms. So normally we will start the libraries using the library by importing the models, all of the models, using this command from GOP import models. And in order to create an instance of a model, for example, we want to create an instance of a POP algorithm, then we will use models.pop. And to get the default parameters, which is a Python dictionary, we will simply call the method getDefaultParameters. And to train the model, we will use the fit method here. This fit method using three main parameters, that is params, the data func, and data argument. I will talk in more details about the fit method later. And for saving the trained models, we can use the method save with the file path to the name, the local file. And also we can reload a safe model using the load method. So for all of the algorithms in our library, we expose the same interface, common interface as you see here. The complete description of our common interface can be found in our documentation page. So now let's take a look at the documentation page. Here you see that under user guide, we can come to the common interface sections. Here we discuss the common parameters, which is used to configure the algorithms. Here we list out all details about the common settings of all algorithms and parameters. In addition, we have the documentation for each method in the model, like the fit method, the fine-tune method, the evaluate, the predict, the save, the load methods. So in each sections, we have the name of the method, and we have the arguments of the method, also the type of the output that it returns. So when using our libraries, and if you are not sure about anything about this common interface, you can consult our documentation in the following sections. Now, since you've seen the common interface, I will talk more about the fit method, especially the model parameters. So the model parameters It is a Python dictionary. This first parameter is a Python dictionary. It contains model-specific parameters such as the learning rate, the epoch, the type of regularizations, the maximum architectures, the number of layers. All of these information will be configured using this dictionary. And these parameters, we can get a default one by calling the getDefaultParameters method. And the complete description can also be found in our documentation. Let's take a look at the section called Common Parameters. Here you see that we have many settings or many fields for this dictionary. As a brief look, for example, we can set the temporary directory, the model name, the input dimension, the output dimension, the set of nodal operators, the pooling operator, the activation operator, the matrix, and so on. So all of these are required to configure a model, and you can get the default one by calling the getDefaultParameter methods. And usually what I usually do when developing algorithms using our library is that I will call this, I will create a default parameters, and then I will start to modify those configuration that I want to change. For example, the learning rate or the number of epochs. The second things I want to talk, and also important in our library, is the data fitting mechanism. So in our library, we implement an efficient data fitting mechanism here to train and evaluate the models. As you see, data func, it is a Python function, and it should take a data argument as input, and it should return a Python generator and the number of steps, also known as the number of mini batches in an epoch. For example, if our data has 100 samples and each mini batch has 10 samples, then the number of steps is 10, or the number of mini batches is 10. The second argument is the data argument. It is the input to the data functions. It can be of any Python data type, for example, list, tuple, or dictionary. So here's a few tips when you implement the data fitting mechanism. For the data argument, we recommend, because it is serialized during the implementation and the run of the algorithm, it is serialized and distributed to different workers in the machines, in the local machines, or in the machine within the clusters. Then it should not contain the actual data, but rather it should contain the metadata, for example, the path to the file in a local disk, and the actual data reading and processing mechanism should be implemented in the data functions. Now, let's take a look at the implementation of data func and data argument. Here you will see I have a simple data func implementation. This data func function takes as input the list or tuple of two variables, the file name and the batch size. The file name, is the pico file, which is used to save the data as a pico format. And inside the data func, you see here I read the data by loading the pico file, and the data, as you see, is a dictionary that contains the inputs and the labels. And here I get an instance of the generator, the data generator, given the inputs data, the label, and the size of the batch, of the mini batch. And in this part, I calculate the number of mini batches given the batch size and the number of samples. Here, we assume that the first dimension of the input is the number of samples. And here I calculate the number of mini batches. And as you remember, data func should return a generator, a Python generator, and a number of mini batches that is required for to complete one epoch. Let's take a look at the implementation of example generator here. So for example generators, it takes as input the input data, the label, and the batch size. Here we assume that the input and the labels are the NumPy arrays. First, I also calculate the number of mini batches here. And then if you are familiar with Python generator, then you know that it always contains a for loop, a while loop that runs forever, so that the generator can generate data infinitely. Here I generate the indices of the samples in the data, and then I sub for them. This is especially useful for the training data because we need to introduce stochastics for backpropagation algorithms. And then we go through for every mini batch, then we calculate the starting index and stopping index of the sample in the data, and then we get the mini batch data in terms of X and Y here. And here one can implement any potential processing step, for example, normalizations. And then we return the data with the comment yield, which is the syntax of a Python generator. So this generator, every time we call the next method, it will generate a mini batch of data in terms of X and Y. So this is, you can see it can be used as a boilerplate or a template that can help you start with writing your own data generator and data function. In the documentation page, I also have very detailed description of this data generating mechanism. It is called data fitting mechanism. And here I also write lots of explanations for every line of code here with some notes and tips on how to write efficient data generator. So this is exactly the example that I've shown you before. And let's now take a look at a real example that is used in our face recognition experiment with the CoLab A dataset. So under the example directory, we can go to the data utility file, and we can see here is the example of the data function. It's called load mini CoLab, and it receives the argument, the file to the inputs, the file to the label, the size of each mini batch and the option whether we do subfold the data or not. So this implementation is used for both the training data, for the validation and the test data, because usually during training we want to subfold the data, but during validation and testing we don't need to subfold them because we only evaluate the data. And here you can see that X file and Y file is a NumPy array file, and here I load them inside the data function using NumPy load functions. I also calculate the number of steps or number of mini batch here. And here I directly implement the generator inside the loop. The definition of data function, as you see, we also have the while loop that runs forever. And we check if whether we do subfold the data or not, depending on the subfold options. And we also generate mini batch of data here. And the data function should return the generator and the number of mini batches. So this is the real example from our tutorial, from our experiment using the mini CoLab A dataset. Now we take a look at a code example. In our documentation page, we have two examples for our library that you can just download the code and experiment yourself with the example code. We have the code for the MNIST dataset, which is the digit recognition dataset. And we have example code for mini CoLab A dataset, which is the face recognition data set. Now let's take a look at the example code of the two experiments. It is under the tutorial section on the left hand side menu here. So if you click into the face recognition with CoLab A dataset, here I have details information on how to prepare for your experiment. For example, you need to get the source code. For this particular example, we need 3 files, which is prepare mini CoLab A, the data utility file, and the main training file. In addition, in order to run this example, you also need to download the extracted data that we have prepared by clicking this link, and you need to extract it to the same folder that has the source code. So if you also want to do the data extraction by yourself, then you can also download the raw data and use our script that we have used to extract the D features for this data here. Let's take a look at the code itself. Here you see that I have downloaded the data and extracted in this folder called data. Inside this folder, you will see 6 NumPy files, the Xtrain and Ytrain file, which contain the input and the label, the test data, and also the validation data. All of them are in NumPy format under the data directory. And you see that this directory should be at the same level as the example code. We need the data utility file, the train mini CoLab file, and the prepare mini CoLab A file. And all of these 3 files can be obtained in our GitHub repository under the directory examples. If you click in example, then you will see these files under the example directories. You can download these files from here, and then you can try out the experiment that I will show you now. Let's take a look inside the train mini CoLab A function script. This is the main script to run the experiment. Inside this script, I import the data utility functions or package and other things. And also here I import all the models. And the uses of this script is that you will run the following command with given the option about the type of the model and the type of computation that you would like to use, whether it's CPU or GPU. And here the type of model, it is the name of the model or the type of algorithms you want to use. In this part, I pass the options given by the user. In this part, I specify the input dimensions, which is 512 features extracted from a deep network, and the output dimension is 20. In this example, we are trying to classify 20 different identities based on the facial images. And here we try to configure the computation. There are two types of computations. The search computation, which is used during the operator set evaluation process. As you remember previously in the presentation from Professor Iosifidis, we need to evaluate different operators in the operator set library and select the best one for a block or for a layer in our algorithms. And the search computation is specifying the type of devices to use during the search process. Here, it is a tuple of the name and the number of workers that will be used. If it is CPU, then I simply write CPU, and here 8, it means that I will use 8 workers, 8 parallel workers for the computation using CPUs, and these ideally should be set to be equal to number of CPU cores that you have or number of threads in your current machine. Or if you decide to use GPU, then you should give a list of the GPU number. Here, for example, one machine can have 4 GPU and I would like to use all of them, then I will specify a list from 0 to 3. And the name, the index of the GPU, it starts from 0, not from 1. And for example, if your machine has only 1 GPU, then you should give a list of only the first GPU, which is 0. Or if you are using a share machine and you know that your colleagues are using GPU 0 and you want to use GPU 1 and 2, then you can specify 1 and 2 here. In this part, I pass the name of the algorithms and create the corresponding class of the model. Here you see all the options. We have POP fast, POP memory, 2 variant of POP memory, and the heterogeneous GOP here. And here I create an instance of the model. In this part, I create the model name for the experiment, and I get the default parameters, which is a Python dictionary, as I mentioned previously. I get the default one, and also I create a temporary directory. So inside this temporary directory, intermediate computation result will be saved to this directory. That's why we need to specify the temporary directory for the algorithm to run, which is temdir and model name here. Both of these configuration is required to create a temporary directory for the given script. Here I also specify the input dimensions and the output dimensions. Because we are doing face recognition, which is a classification problem, then I specify the matrix, which is accuracy, but you can also specify more matrix, for example, mean square error here. And this is a classification problems, so I will use the cross entropy functions, and the name of the cross entropy function in Keras package is categorical cross entropy. For the loss functions, for the activation function, I will use softmax. Here, convergence measure, it means that this is the metric that will be used to monitor the progress of the network growth. When we build a network, we will need to specify whether we want to use what kind of metrics, what metrics we need to use to monitor the development of the network growth. Here, one can also specify, for example, mean square error or categorical cross entropy, but because ultimately we're interested in accuracy, so I specify accuracy here for a convergence measure. Here the directions I specify as higher. It can be higher or lower depending on the type of convergence measure that we specify. If we are using accuracy, we should specify higher. Here it means that the higher it is, the better. And if we are using mean square error here, we should specify the direction is lower so that the algorithm knows that lower mean square error means better network. Here also configure the search computation, the fine-tune computation, the output activation. Here also we have option to do regularization, for example, input dropout or just drop out for the network. In the intermediate hidden layer, the weight constraint, we specify the maximum norm of the incoming weight to a neuron. Also, we can specify the weight constraint during the fine-tuning process. The type of the optimizer, I will use ADAM optimizer here. The learning rate and the number of epoch during training and during fine-tune. When you are writing and debugging the code, I suggest that you will reduce the number of training and fine-tune epoch to small numbers. Here I put only 4 epochs. The first 2 epochs will be trained with the learning rate 0.01, and the last 2 epochs will be trained with this learning rate. So the left of the learning rate, because we didn't specify the number of epoch, then it will not be used. But here we can modify it to the smallest number, which is 1 here for a fast demo. The direct computation option, it allows us to compute the least square problem, whether we want to do it iteratively or in once. So here I want to do it in once, which is more memory intensive, but because we are using a very small dataset example, then it will be fine. Here I specify the number of maximum block per layer, which is 5 block, and the size of the block, which is the number of neurons per block, which is 40. So this means that the maximum number of neurons per layer is 200, and the maximum number of layer I specify here is 4. This max topology properties is only required for the POP and POP fast and POP memory algorithms. For heterogeneous PyGOP, we only need to specify the maximum number of blocks, the block size, and the maximum number of layers. And here I put the batch size to 512. Here you can see the main script, the main part that I use to fit the model using the configuration parameters, the train function, which is the data function, and the data function, which is the load mini celeb A function that I have shown you before from data utility, and the train data, which should be actually be metadata, is a train argument. And as you see in train argument, it specifies the file to the input, the file to the label, the batch size, and the option whether to shuffle it or not. So because this is for training, then I do shuffle the data here, but for validation and testing, I don't do any shuffling. Also here, our fit method for validation and test data, it is optional argument, but if you give the validation and test data, then for every computation step, we will also evaluate the performance on the validation and the test data. And here, one point I should note that if you specify the validation data, then the growth process, that is the decision whether to continue building more blocks or terminate the building of the network, it depends on the validation performance. So if we are improving the validation performance, then we will continue building the topology of the network. But if this is not given, then our algorithm will depend on the training performance. And the test data we only use to measure the test performance and report later. After that, you see here, I create a text file and save the training time and also the performance in this text file. Now let's take a look and let's try to run this particular example. So here you see I need to activate the environment, the PyGOP environment for GPU. Before running any GPU experiment, it's always good to check which GPU is available with this command. As you see, we have 4 GPU in our machines and all of them are available. So I will use all of them. So let's try to modify here the GPU that I will use all of the GPU. And let's try to run the heterogeneous GOP algorithm, which is a fast, efficient algorithm in the set of algorithms in our library, is also the most recent one. So here I call Python and train mini celeb, and this script, it requires 2 user given input. The first one is the type of algorithm, so we're using heterogeneous GOP. And secondly is the type of computation, and I will use GPU here. And because during training, the script and also this TensorFlow and Keras, it prints out lots of warnings. So in order to direct all of the warnings, then I will direct the warning to a text file called error.txt here, so that when you run this, you will only see the output. So you see here, it starts to run iterative random search in the heterogeneous group algorithms, and we're using 4 GPU, and here we see the status of the 4 workers on 4 GPU, and as you see here, we are using a total of 144 operator sets from the default libraries. Here is complete the first block. We can see the train loss. It prints out the matrix, the training loss, which is the cross entropy loss, training, validation, and test, also the accuracy as we specify the matrix. And because we also specify mean square error as the matrix, we also see it print out here. First, it starts from layer 0 and block 0, and then it continues to the second block, which is layer 0, block 1 here. So now you see it go to the third block. I will show you one features of our library is that if now I decide to terminate the script now, you see I've just pressed Ctrl+C and terminate the experiment. Or in case you have problems with the servers, the computers, then now if I clone the script, the code again, run the code again, it will start again from block 2. So all of the intermediate result, it is saved to the temporary directory that we have specified before. And when we call, if we don't modify anything and just run the script again, then our library automatically find for the checkpoint and resume the experiment from the last block, which is block 2. So running this demo, it would take a few minutes, but now I think it's a good time for you to try out what I've just experiment with this code. And if you have any intermediate questions, I really recommend you to ask now.
Participants, if you have any doubts, you can ask. Nothing, sir. No questions.
Now, if you take a look at the performance, because we are having the validation data, so what we should expect from our result is that the validation accuracy, because we are monitoring the convergence based on the accuracy metrics, and because we have also validation data, then it should be based on validation accuracy. Here for the first block, we have validation accuracy of 81.83. For the second block, we have 89.17. For the third block, we have validation accuracy of 92.50. So you see that the validation accuracy is increasing as it is expected. And if this accuracy stop increasing, then our algorithm will terminate the progression within the current layer, which is layer 0, and continue building the next layer. In the meantime, you can ask any questions, or if you have any problem setting up our libraries, you can also ask about it. This will take us a few minutes after it completes the first layer and the second layer. So here you see, because we specify maximum of 5 blocks per layer, when it trends to the last block, it still increase their validation accuracy. So it continue building the second hidden layer. As you remember, because I'm running this demo with just 2 epochs for the fine-tuning process, for the fast demo, but what I recommend is that you put the number of epochs for the fine-tuning to few hundred epochs, so that if you put it to higher number of epochs, then you can have better performance at every progression step. In this way, then you can get very compact network, final compact network in the end. One thing here we can observe is that when it transitions to the second hidden layer with only 1 block of neuron, then we see that the validation accuracy, it drops. But this number is not used to compare to the previous number, because we are now just starting to build the second hidden layer. It is only compared to the previous layer when we completely build the second hidden layer, as you will see in a few minutes. I think in the meantime, I can also go through the code example from the MNIST dataset for you. So here, as you see from our documentation page, for the MNIST dataset, we only need a single file or a single script called train MNIST under the example directory, which is train MNIST here.
There is one question from, sorry to disturb you. There is one question in the chat box. Hello, sir.
Yes, okay. Sorry, I didn't see that. It is the question
Sir,
is
as
in.
I see you have four high-end GPUs, most probably GTX 2080 Ti, and my laptop has only one GPU, that is GTX 1650. So will it significantly reduce the speed of training?
Yes, that certainly will slow down the experiment a bit, but because the demo that I'm showing you and also the example I'm showing in our library, it's very small. So I think the differences is not very big in this case. Also because I'm fine tuning the network with only 2 epochs. So it's the differences I think is not so significant. You can also try it out with just one GPU, but remember to modify the code so that in the source code you only specify one GPU from the code examples, because it is written in the code example that it used 4 GPUs in my case, but because you only have 1 GPU, then you just need to specify it is using GPU with the least of 1 GPU.
Okay, sir, I will specify only one GPU in Google Sensor. Gaussian, I think your doubt has been clarified.
Sorry, can you speak louder, please?
Yes, sir. Gaurav Singh is saying that he will specify only one GPU. His doubt got clarified. Thank you, sir.
Yes. Okay, here let's take a look at the data function of the MNIST experiment. Because the MNIST dataset, it is available from Keras library, and because Keras is one dependency of our library, then we don't need to download the MNIST dataset, but we will simply load the MNIST dataset from Keras. So here you see the data func example. It received an input, 2 variables, the batch size, and the name of the split. And here I load the MNIST dataset from Keras, and here based on the split, whether it is the train set or the test set, then we will select the corresponding set of variables. And here I also convert, because it is the label, numerical label, then we need to convert it to one hot vector of classes using this function from Keras. And we have 10 classes of digit here. Also, the MNIST dataset, it is originally images, so it is a matrix. So we need to reshape the matrix to a vector form, 28 by 28 here. And I also define the generator in this part with the while loop and the indices of the data and sub for them if it is the trend set, and generating mini batch of data with the corresponding index of mini batch, and finally return the generator and the number of steps per epoch. Also, if you take a look at the full experiment code, I have very similar structures to the face recognition dataset in the main functions. I also parse the type of the model and the computation options. Also specify the input dimensions, the number of output dimensions, and the option for computations. Also, based on the model name, then I create a corresponding instance of the model and create the default parameter and start modify them here. As you see, normally we put the number of epochs to few hundred epochs for the fine-tuning process. Also during the fine-tune during the train process. And the rest of the script, it has very similar content to the one that I've shown you for the face recognition experiment. And here, as you see, our experiment has completed. And the last block that is evaluated is from the second layer. And the last block of the second layer, the fifth block of the second layer. Here we can check out, after building the second hidden layer, we have the validation accuracy, which is 86.83, and comparing this to a network with only one hidden layer, which we can check from layer 0 and block 1. This is the last block in the previous hidden layer. We achieved 93% of validation accuracy. For this reason, adding a second hidden layer reduces the validation performance. And the algorithm, it compare the validation accuracy between a one hidden layer network and a two hidden layer network. And here we have a one hidden layer network which perform better. So in the end, the algorithm just discard the second hidden layer and perform fine-tuning based on a single hidden layer network. And because we only fine-tune for 2 epochs, then the validation accuracy still stay at 93%, as you see here. So this is the final performance. After fine-tuning, the final performance with the training, validation, and test loss is this, and the accuracy is this, and the mean square error is this. So as you see, when I reduce the number of epochs, it runs very fast for the demo, but in actual code, we should put more epochs for the fine-tuning and also for the search process. Now I will come back to my presentations about miscellaneous things with our library. The first one is that at the moment, what I've presented you is using built-in operators of the libraries, which is specified in our publications. And if someone wants to use custom operators or custom metrics, for example, if you remember the previous presentation from Professor Iosifidis, for financial data, we need to use spectrometrics, which is precision, recon, and F1. These kind of metrics, it requires the full batch computations. So for example, for mean square error or accuracy, we can compute it based on mini batch of data and then accumulate the metrics. But for precision, recon, and F1, for example, it should be computed based on the full data. So we have the flexibility to do lots of customization with not only the operators and the matrix, but also the loss functions. I will show you the section in the documentations about customizations. Here I have very detailed description of how to do the customization. For example, here we have custom loss function. This is the list of the loss function that is natively supported by our libraries. You see the list is comprehensive, but we always want to tweak and to build and experiment with new type of loss function. So we cannot always accommodate all of the loss function. And in order to define your own loss function, you can specify your loss function to the field of the parameters dictionaries. And if you have a custom loss function, it should have this template. It should receive two arguments. The first one should be the true label. The second one would be the predicted labels. And then you perform the calculation within the body of this function. And remember that the two variable inputs here, it is the TensorFlow tensors. So you should use the function to calculate the loss using TensorFlow or Keras backend operations. And for the loss function, it should return a scalar, which is a single float value. So here I have an example of a custom mean square error functions. And here I assume that the first dimension is the number of samples. And what this function does, as you may see, is that it first computes a mask, which will be 1 for those samples that has the same sign of prediction between the true label and the predicted label. So the predicted value, if it has the same sign, plus or minus, compared to the true sample, then we will select them to calculate the mean square error here using TensorFlow operation, the sum and the flatten operation here. And when you define your custom loss function, and you simply specify it in the parameter dictionaries. Beside the loss function, the matrix function can also be customized. So here's a list of built-in metric function in our libraries. And we can also specify our custom one very similar to the loss function. Here I use the same definition because usually we have the loss and the matrix, which are similar, but the loss is used to optimize the network, but the matrix is used to monitor a certain performance of the networks. So for the matrix, you need to specify the list of matrix. And here you see that I used a combination of built-in metric function and the custom one, and specify it for the matrix property metric field of the dictionaries. For spectrometrics, that is those metrics that require the full computation of the data. For example, precision, recall, or F1. Then you need to specify it to the keyword spectrometrics in the parameter dictionaries. And here I show an example how I can use the function from scikit-learn library to compute precision and recall, and use it in PyGOP libraries and specify it under spectrometrics here. As you see here, I simply use the function from sklearn and use it, combine it with our PyGOP library to have a fast way to have precision, recall, and F1 computed. Although these functions are not natively supported by Keras or TensorFlow or by our library, but you can easily implement it using a third-party library by this way. Also for the custom operators, here I list the template for the custom nodal, pooling, and activation operators. You should consult this part because it has certain specifications on the shape of the input. For example, for the pooling operations, that it should be tensor with 3 modes or 3 dimensions, and here I specify what should be the first dimension, what should be the second dimensions. Here, for example, the custom pooling operation, I simply implement the summation operation for the pooling. For the activation function, it's simply any operation that operate on each element of the given input matrix. For example, here I use the sigmoid function from TensorFlow, and for the nodal pooling and activation operators, all of them should be implemented using the basic TensorFlow operators. So that is for the customizations. For computation environments, as you might recall, we have support for CPU and GPU environment, but we also support for a cluster environment that have multiple machines running on CPU or GPU using the Slurm scheduler. So Slurm is a very popular scheduler used in academic and also industry environment, cluster environment to manage the clusters. So if you go to computation environments, here I discuss in details how we can specify or configure the computation environment for a local machines like local CPU, as I described before in the example, or local GPU, and even for the cluster computations, how you can configure by turning on the cluster option and giving the batch job parameters that is specific to Slurm scheduler. This is Slurm. This is one of the popular scheduler that they are used in the cluster environment. So we have native support for the cluster environment to Slurm, and you can easily specify the Slurm parameters through these batch job parameters and turn on the cluster options here. Here I also have detailed description of what should be configured for the batch job parameters, such as the name of the job, the size of the memory, the number of CPU cores, the partition of the clusters, and the maximum time that the job will be run, the number of machines or the number of nodes to be used, and the custom Python command that will be used to execute your Python script in the cluster environment. Here also have additional constraint on the hardware. For example, we are using GPU or CPU, or even for GPU that it might be different architecture for Intel GPU. Also the configuration, such as we want to turn on certain environment, like setting up the path variables. So all of these are very detailed under the section computation environment of our documentations. Finally, I think when you get used to our library, you will see that there's a lot of contribution you can make. For example, algorithmic contribution. When you come up with new algorithms, you can easily use our built-in functions to develop your own algorithms. And you can also make it publicly available also under our library by making the contribution to our package, so that we will consider adding them to our PyGOP libraries. In order to do so, I also have a section how you can do contributions. So because our GOP library, it is hosted in GitHub, so we normally follow the procedures in GitHub using the PR mechanism, which is pull request. When you have any request on, or if you figure out any bug, you can perform bug report. So in this bug report, you can create an issue in GitHub and describe the type of issues, the configuration of your system, all necessary details so that we will know what kind of environment that triggered the bug. Also for pull request, you can send me an email if you want to contribute to our code base with the subject Python development. And for doing the pull request and contribution, source code contribution to our GitHub, then you should establish another branch, local branch from our GitHub. And also remember to hook it to continuous integration service. For example, Travis, write your code, write your unit test before you make a commit and make a pull request, and send me an email also at the same time. So this is all of it. But one last reminder is that if you used our libraries, then you can also cite our libraries. We have this library also comes with the publications, which is in knowledge-based system journal. So this is the associated publication of the libraries in knowledge-based system journals. If you're using it, we really appreciate if you cite our publication, our library to these publications. And finally, thank you for attending my tutorial, my sessions. If you have any questions now, I can try to address it.
Participants, if you have any questions, please post it in chat box. Raghu sir? If you have any doubts in this demonstration, please post it in the chat box.
Okay, so there's one question about NLP sample code. At the moment, I don't have any sample code, but if you are working on NLP problem, I really advise that you try out our algorithms, and also you can contribute the sample code in the libraries. And of course, we will, if it is working fine, we will include it in the library, and also, of course, mention you as a contributors to that sections.
Any more doubts? There is another question. Okay, thank you, we'll try. In MNIST code was CNN used?
So in MNIST code, well, I should remind that all of the algorithms in GOP, in PyGOP libraries, is for feed-forward fully connected network. So it is not CNN, but we simply use the vectorized images of the digit image, and we vectorize them and use them as the vector, not as we don't use any CNN to extract the features. But for the mini CoLab A experiment, we used the image data, we extracted the D features using CNN, and we use the features from the CNN as a vector to feed into our algorithm. So in the code example in our documentation, you will find the code how to do the extraction of the D features, but I also include the extracted features as a zip file and as a compressed file, so you can just simply download it in the matrix file, the numpy file, and you can simply use it with our algorithms.
Okay, sir. Thank you for sparing your valuable time with us and sharing your valuable knowledge with us, profound knowledge with us. A very good demonstration of this PyGOP library research. We are very happy for being with us. We have a small token of appreciation for you, sir. Please accept our appreciation. The certificate
Yes,
will be mailed to you.
thank you a lot for inviting me to these sessions and allowing us to present our work. I really appreciate.
Thank you, sir. Thank you, Alexandros, Iosifidis, sir, and Dat Thanh Tran.
Thank you very much.
Sir, will you share these slides with us, sir?
Yes, I can. For me, I can share my slides, and all of the example are also in our documentation page online. So yeah, it's already public.
Okay, sir. Okay, sir. Thank you, sir. So participants will have next session will start within 5 minutes.
Over a period of these 3 days, you have been hearing from various experts in this field, from Akira Hirose to today's Alexandros, the developments in ANN and how ANNs are being widely used today. Okay. However, my presentation is towards the very basics of a particular application that we have been going through. That is how we can model an epidemic using artificial neural network. So this topic I would cover with some bit of mathematics that I will present, but it's a few equations, nothing more, and then how ANN has been used and what for, why not the other kinds of machine learning tools we have. So these aspects I will throw some light on it so that we can have, again, better appreciate the ANNs and its use. Okay. I have to share my screen, right? If I run my PPT and then I can share, no, Shweta?
Sir, share screen, sir, that's it.
Share
Open
screen, but I have to run PPT in the background.
Yes, sir. Open PPT
Okay.
and just
Okay, 1 minute. PPT is loading. It's heavily raining outside and was very hectic task for me to get back on time and load the system. 1 minute. Okay. PPT is loaded. I'll just share my screen. 5. Okay, you're able to see the screen?
Yes, sir.
Okay. So my topic of presentation is predictive modeling and how artificial neural nets can be used for predictive modeling, and a simple use case I'm going to take to showcase how an ANN can be used. Okay. So what is basically a predictive model? We need to understand that. So before even predictive model, we need to know what is a model means. So basically model is an abstraction of a real world process. So what is a real world process? What is a process? Process is something which has an input and an output and some in between actions to transform input to the output. So this is basically a process. So the difficulty with the real world process is the type of inputs and the type of transformations that happens is complex. Means it's not really very easy to understand how the input is getting transformed to the output. But if you observe the process and try to create an abstraction of that particular process, then we call it as a model. So a model is becomes predictive only if we are able to, yeah.
Sir, sorry to disturb you. Can you please make it full screen, sir?
Full screen.
Slide
Okay.
F5.
Okay. Is it okay now?
Just a second, sir. No, sir.
I have made it full screen.
Or make it slideshow, sir. Slideshow.
Yeah, I have done slide F5 slideshow. I have done. No. Now.
Once. No, sir.
No. But here I am seeing slideshow only.
Yes, sir. It is also. It is saying exit. Already full screen is there.
Okay. Should I say slideshow again?
Yes, sir.
Now.
No, sir.
No.
Once stop sharing and again open.
Okay. Reshare.
Just a second, sir. Another message from that. No problem, madam. Continue, please. Okay.
Okay. So basically, the predictive models provide an outcome, a decision. Like Professor Risto's talk yesterday, we have seen prediction is different from decision. So right now we are only talking of a prediction. That means the model tries to generate an abstraction of the process, and then based on some data tries to predict, means say what could be the future kind of situation. Like there is a slight difference between prediction and forecasting. Generally, when you say prediction, that means you are not talking about the you are giving a, like, yes or no kind of a what would be the next state. But when you say forecast, you can talk about next few days or next few, whatever the time step is, like a few hours or something. You can forecast all the values that is possible. So when you say predict, you are able to say the next step, only one future step you are trying to talk about, what would be the model outcome if these are the input values. Now the important aspect here is how good is your model, because since you have done abstraction, you would not be capturing all that happens in the real world process. Okay, so that means if I say there are certain in the COVID-19 situation, Professor Risto's talk, we spoke about several controls that are being done, like for example schools are closed and things like that. There may be some other controls that may be happening, but we may not have captured that, and that may be contributing some better understanding of the process. In that case, our model predictions will not be accurate. So one thing is to see what data talks about. The other one is model using some kind of a learning from the real world problem and creating an abstraction of your own. So when you do that, we call it as a mathematical model. We are not dependent on the data. Whereas data driven models requires a lot of data, and the data something like what we call, if you give a garbage in, what you get is a garbage out. So we should be very clear about what is the data, what we are giving in, and what kind of any kind of data outliers and data noise. So many things are involved in that. So how in a noisy environment these models perform, that is of very critical importance when we talk about predictive models. Okay, so one is how near are we to the real world measurements. The other one is how to optimize, how to make it a better estimate, or how to tune so that your model represents the real world outcomes. Okay, so that is about the predictive model. So when you come to the mathematical model, okay, just because we need to understand what is an epidemic. Without understanding what is an epidemic, you cannot have an ANN or some kind of a machine learning algorithm to do something for you. So people are sometimes simply taking some data and then trying to churn out some output without the knowledge of the model itself, what is actually happening. So here, what is an infectious disease? I will just give this only one slide, not very complicated math here. Okay, so this infectious disease is one which basically has certain rules for transferring one to the other. So these simple rules one need to understand. So for that, let us see what are these simple rules. So there is certain population, and this population, at least one infected person must be there for
Your
the
slide is
infection
not
to spread.
moving, sir.
Not moving. I think it will refresh. Let us wait. Anyhow, you can listen to my voice, right?
Yes, yes, yes.
Let us simply listen to that, what I'm saying.
Okay.
These slides anyhow will be shared. That's not an issue. So the susceptibles are ones who can be infected, right? So here there is no prior kind of a what we call antibodies within them that they don't get the disease. Some immunity kind of thing is not there, let us assume. Then everybody can become infected. Okay, so and also these susceptibles we have to assume that because there is no natural immunity since a new virus has come in, so these susceptibles are also fixed, they are not moving. That means let us say if it is a floating population, then our assumption, our models will not stand right. Okay, so we will say the total population is fixed. Otherwise, you are people flying from here and there, moving in and around. Then this becomes a very complex problem for the mathematical modeling. Whereas database modeling, we can do that. Okay? And disease spread happens only through contact. That means one infected person comes in contact with one susceptible persons, then X number of people gets converted to infective. X number of susceptibles gets converted to infectives. That means X1 susceptibles are there, and then if X2 susceptible infectives are there, then X2 will convert X1 as infectives. So this is the kind of a simple model that we have tried to model, try to see here. Okay, and another thing is assumption is once an individual gets the infection, then he would not get reinfected. Anyhow, this is a very simple assumption, but sometimes it may not hold good. In the recent COVID case, what we have seen is reinfection is also happening. So presently the model I'm going to talk about is very simple because this will help you to understand what we are going to do. Okay, so we have now the two compartments will be there, because this is called a compartment model because we are dividing these populations like susceptible population and infective population as two compartments, and people move from one compartment to the other compartment based on the infection rate, the rate of infection. So you will get two simple differential equations: the rate at which susceptibles become infective and the rate at the infectives become recovered. Okay, and some deaths may happen. So that's why you have x1 prime and x2 prime are two differential equations that will occur, and there is an infection rate, a rate at which x1 is converted to x2, susceptibles are converted to infectives, and then the susceptibles are removed from the equation, first equation, because they are becoming infective at some rate, let us say. So S of x1 is a function on susceptibles, and we have infectives. The rate at infectives are being removed from the population either because they are cured or because they have recovered. Okay, or recovered or cured, or they are dead. So whoever is coming from the susceptible population, they will be added into the infective population, so that the total population is a constant. Okay, so these are a simple compartment model, and then there are some assumptions that the susceptible population should be greater than 0, and at least the rate at which susceptible becomes infective, there is infection to be sustained, so the population should be greater than 0. Okay, now this, once we understand that particular process, let us see what ANN would do and why ANN. First of all, we should know why ANN we should use and what is ANN. So basically ANNs are something like a model for that is again an abstraction of how the central nervous system works. And just previously you have seen the Alexandros presentation, where you have the dendrites, the axons, and then the connection with other dendrites. There is something like a band gap, and I don't know whether this band gap can be assumed constant or it will vary with the different types of axon dendrite connections. Okay, so there are so many still we have not modeled from the human central nervous system is concerned, but there's a lot of development we can do once we enter into start working with ANNs. So let us see a simple ANN where there is a neuron, and this neuron receives input from several other neurons through these axons, dendrite connections. Okay, And then all these inputs that are collected will either fire the neuron or will not fire the neuron based on its activation. Okay, so let us say kind of a logic where you have a plus 5 volts input that is to be given. If plus 5 volts, if you exceed the input, then you get a output, otherwise you don't get an output. That kind of a logic if you build in. So this neuron can be thought of such a kind of let us say a device. Okay, the connections are like dendrons, as I said, and they help in carrying the information to the neurons in a network. And as I said, there is a summation that happens at the neuron, and you can have different activation functions as Alexandros was talking about in COP. Okay, but the selection and which type of activation function is there, all these things are left as some kind of a logic which you can pick up. So now the advantage of an ANN is basically being a black box. So a black box means you have a neural net, you give some input and you get output, and then what happens inside is still a mystery. You need not know. It's one advantage. You don't know is also a disadvantage. So there are two sides of the coin when you are doing artificial neural nets. Okay, and again, easy to train because we have a simple neural net. If you take then you can use any gradient descent algorithms you can use and try to train using backpropagation, or you simply use it as a feed-forward network. There are so many variations of that and so forth. But the speciality of ANN to solve nonlinear problems is because of the layers. Okay, so this hidden layer, once we introduce the number of hidden layers, the more kind of nonlinearities we can handle. So that is another advantage. But how it is encoding this nonlinearity is not very clear. There are several studies that has been done that see, everything revolves in ANN around weights. Okay, whatever may be the kind of activation function you choose, or real U or whatever kind of activation function, sigmoid, tansig, whatever it is, the weights play a main role. How do we initialize the network, and what sort of weights we have to take, and how do these weights interact? And this is a very interesting to see, can we trace back the rules from these weights? See, I want to go back. Let us say I have made a selection at the output. I have trained the network. Once the weights are stabilized, I want to go back and see which inputs are actually responsible for this output. Okay, so these type of studies that would be of interest, and there are several such examples, like creating a decision tree from ANN, and such types of interesting research is available. Okay, so we will look into those aspects as we proceed, maybe in some lectures further. Just I will join in 1 minute. Okay. Okay, sorry for the small hitch. So this multiple layers and different activations, and different types of like deep neural networks or convolutional neural networks. So if you add convolutional layers and then autoencoders, so different types of networks have come into picture for both supervised and unsupervised kind of situations to handle. So that led to resurgence of ANN. Actually, ANN was sidetracked. It ended with multi-layer perceptron and such type of things. But with one path-breaking algorithm known as Boltzmann machine, which led to like cognitron and neo-cognitron. These kinds of networks have come, then started the deep neural net. I think this reference you can find in Akira Hiroshi's presentation, if you see how the deep neural nets have evolved. And then came the complex valued networks and such kind of things for specialized application. Like in fact, spiking neural nets are also one of these class of networks, which we are not covering in this. Possibly in one of the other course when we create, we will call experts on spiking neural nets. Okay, these are all different variations of the neural networks. So there is presently great demand for these ANNs. And in fact, the last presentation was very good for most of the practitioners. They can download all the code and verifiable with the kind of outputs that is generated. So this gives you great learning. So do download that PyGOP and then try to see what it says about. But there is a pitfall. No doubt you might have seen different algorithms of ANN being trained. What I see is still they are not outperforming for all data sets. That means we are not creating a generalized model. We are still looking at some specialized models which work for specific data sets, or you can train it for specific data sets. Okay. And generally, as I was talking about, it requires large data sets for training. So if you have fewer data sets, you are training. In fact, an interesting question to all the experts would have been, what if you have fewer data sets? Fewer data sets will happen, especially in the medical domain. Okay, you have, let us say, out of 100 cases, only one is positive and 99 are negative. Then how are you going to train your network for such a kind of imbalanced data? How to perfect such a kind of data set. So these are the things that we have to look forward to. Another one is the training time. Anyhow, some people have tried to bring down training time, but what I feel, for large data sets, longer training time and a lot of compute power is required. So all these data-driven techniques requires a lot of compute, and so they go for GPUs and they go for different types of processing things that they would require. But if you see the human brain, it's quite simple and it doesn't take that much time to get trained. But you have a lot of memory, lot of earlier training that you retain. So there is a lot of still many things to model the human brain and the ANN. In fact, research is going on in this. Okay. So as I said, it's a black box, and still we do not know why ANN, how ANN works. We cannot trace back which are the, see, if I have 500 and odd input attributes, which attributes are actually making this particular decision possible, it is not known. Only thing is that kind of a PCA kind of algorithm you use, then okay, some kind of dimension that are important dimensions you are going to take, but really we do not know which we need to monitor, which exactly the feature that we need to look for. Okay, unlike these decision trees and other algorithms. So having seen the positives and the plus and minus of ANN, so I will just look at how we can look at a use case for predicting the, let us say, this kind of a simple infectious disease. Given the infectives, how many susceptibles become an infective is a problem that we are trying to solve using a kind of a known as some kind of a neural network. We call it as a cooperative supportive neural net. It is very simple neural net. Here, what we will do is we will try to use the dynamics of the equation and then generate some data. Okay, so this will give susceptibles and infectives over a time. Okay, So what we will do is here, the problem with this neural nets is that if the data is heterogeneous, okay, then again there will be issues in learning time, or the learning curve, as I said, would be more if you use CPUs and all. Well, I have used these kind of networks very 2012 itself, have been working on this. So what I have done is basically you try to see the 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 number of groups that are heterogeneous, and make heterogeneous things into one homogeneous group. So once you do that, now you have only that cluster which has got minor variations within them, but they are tightly coupled within that cluster, that we use to generate some kind of the susceptibles. Okay, you give an infective and then you say what will be the susceptibles, and then you can train and loop back. Okay, infectives becoming susceptibles. Then these kind of each clusters, once you generate and then you sum them up in the other layer, so you get the susceptibles and the infectives from the ANN. Okay, so once you do that, what we found was the ANNs were actually outperforming the simple techniques, okay, linear, quadratic, or any kind of simple statistical methods you take. It is performing better. This is a simple one what we have checked. Okay, since I want to give only example use case. So that means ANN will certainly outperform these techniques if it is trained in this particular manner. We have tried to train with the whole data set, but the training, either overfitting happens, or the ANN will not learn properly. Okay. So the other aspect, what I'm going to discuss about how to combine these ANNs. Okay, this was a work in 2012, 13. In fact, I am very happy to see Alexandros' presentation that he has moved further and combined these layers. My problem was, if you have a neural net trained for a specialized, let us say, activity. Let us say I train a neural net for one particular task, and then there are certain tasks, and a particular process has number of tasks. Then how can we combine the specialized task learned by the neural net into a single network, and then obtain a outcome for the entire process. Okay, so what has been done is, basically on the fly you just generate a neural net, okay, and then try to train that particular neural net, and then see if that neural net achieves certain MSC. Okay, error is minimized, and then you create another neural net and see if by combining these two neural networks okay, are we able to improve upon the previous MSC. Okay, mean squared error, if you are able to improve, then include that particular neural net and this particular new neural net into an ensemble. Okay, and then try to again retrain with the combined inputs with these two neural nets together. Okay, so like this you pick up the neural nets till the error remains, let us say, does not exceed certain threshold. So you keep on minimizing the errors till a particular number of neural nets you have picked up, and MSC is not improving. So you have successfully combined the neural networks into an ensemble, and then once you give an input to that particular ensemble, then the outputs are estimated on the from the testing data set, and then the results are very encouraging that this ensemble is able to produce. In fact, the results I have to paste it here, but you can find it in my chapters on dengue and yeah.
Sir, Still we are seeing first slide only, sir.
I have moved to the last slide.
No, sir, only second slide is selected. That only we are able to see.
A window is being shared, control sharing. What is happening?
Go to that particular slide, sir. Click on it.
Okay.
Or else once stop share again, sir.
What is happening? Okay.
We are seeing the window mode of PowerPoint. First open this PowerPoint presentation, sir. Then say share screen. Click on that window.
You are
Okay, sir. Now it is moving, sir. Real world example.
okay. Okay, I have to stop sharing.
Do that, sir, or else just move down, sir. Now it is moving,
Real
sir.
world
Ensemble
example.
ANN. Now it is showing ensemble ANN.
Okay, okay. I think it is not going to F5. What I will do is I will make it 100% or something. You are able to see now better?
Don't let it be like this only, sir. Now you are at the last slide.
Okay, yeah. So an ensemble, the algorithm and the way to build the data sets are all available in the book chapter that is in Springer. You can just see that. And there are further improvements that are possible because the way to combine this is again a challenge. So hopefully that if you have seen the previous presentation of Alexandros and all, we can come up with new network architecture, I think. Okay. So this is about the ensemble neural networks and how a simple epidemic model can be trained, okay, in this manner. So I will stop my presentation here. If anybody has got any doubts, they can just clarify that. I will share the presentation with you all. Yeah. Are there any questions? I'm seeing some. Okay, continue. We have seen things. Okay.
Thanks from Uponika.
Okay, do you have any questions?
What is the application of ensemble, sir, from Uponika, ma'am?
Yeah, see these ensembles, you can use it for, see I've used it for certain application. This is predicting, the dengue. Okay, so this particular disease has got number of parameters. So it's a generalized ensemble is a generalized model which you can use. And in fact, I have applied for this dengue and atherosclerosis disease, how to predict the atherosclerosis disease, because because this is a challenge. It's a horizontal data set. That means you will not know whether you have atherosclerosis means thickening of the blood. Okay, you would not know in a single day, but over a period of time, as you proceed with a certain kind of habits, you are bound to develop this kind of a disease. So there is a progressive one. So there was a challenge of addressing this kind of a data set. So ensemble has done well there, okay, and we have also used it for this dengue disease prediction with number of parameters taking into account. Like a particular person, can he have a dengue if he has these kind of symptoms? Because see, now you have seen the different infectious diseases have got same symptoms, but it is very difficult to differentiate between them. So our model was able to differentiate between the diseases very well. So that is one application where you can look for. And it's a general purpose neural network. You can use it and train it for any kind of data set. Any other questions?
Yes, sir. Any other questions? Participants, please post in the chat box.
Okay, then I think thanks for giving an opportunity to speak
so
here.
much, sir.
Thank you.
For sharing your knowledge on predictive modeling. Sir, I think Tilottama madam didn't join.
Okay.
Yeah, I am here. Hello, good evening, sir.
Good evening, Tilottama. How are you?
Yeah, nice presentation. Thank you. Yeah.
Thank you. Thank you. I have to fill up.
Yeah, you had some work. So can I continue now, or are you going to give the break, or shall I start my session?
We have
What is it, Sudha? Sweta. Sorry, Sweta is there, yeah.
it is, shall we give 5
We can
minutes
continue
break, sir?
break,
Because
okay.
it is still 7, no, sir. 3:30, they are in the workshop only.
Okay, so 15 minutes and we'll start at 6 p.m.
6 o'clock. 6 o'clock?
Yeah.
Yes.
Or else
Okay.
5 minutes
Yes,
break,
sir. Okay.
Okay, 5
6
minutes
o'clock
break.
we'll start.
6 o'clock, yeah. By that time we'll be there.
Okay, sir.
Okay, thank you. We'll
Sure.
join again.
Thank you. Thank you. All have joined now.
Yes, ma'am. Let us hope.
Okay, then I'll start off. Am I audible properly?
Yes, ma'am.
Okay. So this is the Google Classroom where I have uploaded 2 files. One is the presentation file, which you can see here, the CNN1.pdf. And another is the assignment file, which is the IPython notebook. So I'm opening the PDF. I hope it is visible. Ma'am, can you please confirm? Hello, ma'am. Hello, anyone, can they confirm whether you are able to see my screen? Okay, thank you, Sai Kumar. So let me see the chat box here. Okay. So yesterday in the session, we briefly discussed about the machine learning, classification, regression tasks, and also one of the assignment was a classification task. So now this classification task can be achieved using your neural networks as well. So the artificial neural networks, it is basically trying to mimic the human brain, where we are having lots of neurons and the learning process takes place using the various network of these neurons, and some of the neurons get excited or activated depending on the inputs. So the learning process, which mimics this human brain using the computer programming, is achieved by neural networks or artificial neural networks. So in the artificial neural networks, there is another specialized type called convolutional neural networks, called CNN. So first, briefly, I will tell you about the evolution or the history of the neural networks. And then we will see how, as I told you yesterday, that depending on which decade you are there, the tasks become challenging accordingly. So if I go back now to the history of ANN, this one, evolution of ANN, then the same thing, the idea came that how we will try to mimic the brain. So McLaughlin in 1940, they came out with this idea where a particular neuron given an input gets excited or is switched on or switched off depending on some function. We'll go see in details about that. Then the concept of perceptron came. So in this McLaughlin, there was no learning basically. Given some inputs, it was able to classify into classes, that's it. But there was no learning. So if there, because humans, they can learn. So how about the learning part? So there the perceptron came into picture where every neuron is connected to each other with some weights basically. So those weights could be changed. Before that, in McLaughlin's model, the weights couldn't be changed. The weights were not, it was fixed. So if we have learnable weights, then we can say, for example, in our human brain, we remember something and we forget something. How is it possible? So some event which we have forgotten, that means that neuron is not firing. I'm not able to recollect. If I am able to remember some definition and everything, so that means recently I have learned, so that's why we say we have crammed, and we had yesterday night we have learned, and now today morning I remember everything. The neurons are all excited about that. Okay, so now what happens with the passage of time, these weights can make a particular, the weights connected to the neurons are will tell us whether the particular thing, the particular neuron is will be excited or will be lost. Okay, so there is a threshold also. So we average all the connectivities and then we can put it in a threshold, and if it crosses the threshold, then we say that it is plus, or otherwise it is 0. So now what happened in 1970s, if you see the XOR problem. So what happened, all these tasks of classification, they were able to do. So if you see this particular problem of XOR, then across the quadrants, the diagonally, the white balls are there, and the diagonally the black balls are there. So this is called non-linear problem. So non-linear separability is there. And next to it, where you are seeing the 3 black balls and the white ball in first quadrant and the 3 black balls in second, third and fourth quadrant, it is easily separable by a line. So linearly separable. So in 1970, these models which they have come across with the Rosenblatt's perceptron model, they were unable to classify the non-linear problems. So it was not possible. So then there was a dark age and which is also called AI winter, which I mentioned yesterday. So this is the AI winter, and then the scientists Hinton Williams, they came with the multi-layer perceptron. So now this line has come multi-layered. So before that it was only input layer and output layer. And now it is telling that there is a multi-layered perceptron. So in that multi-layer perceptron, yes, it is learnable, it is learning, but there is one, the learning has a very important aspect is using the back propagation. So we will go in details about that. Remember, the multi-layer perceptron learning is with the back propagation of errors. Then slowly we came out with this support vector machine, and there are many other um, algorithms to when you have some prior knowledge, then how do you do the learning, and these things are there. And now finally in this millennium, the focus is on deep neural networks. So multi-layer and deep neural network and multi-layer perceptron. So deep neural network is also multi-layered, but it is deep in nature. And why do we need deep layers? That we will see in the subsequent slides. So as I told you, the perceptron, the Rosenblatt's perceptron. So this is how it looks. There are the inputs. These are the weights. You sum up WIXI, and there is an activation function which says if it is greater than the threshold, then we fire, or otherwise we don't fire. So we trigger binary activations. Okay. So if the sum exceeds the threshold, then we send the signal, and otherwise no signal is sent. So this is a simple learning machine. But as I told you, before this AI winter, the Rosenblatts, they understood that this is only possible for the linear separator. So if you have this AND, if you are able to see, the linear separator works for AND logical operation or logical operation, but it does not work for the XOR. So you cannot put a single line to separate the XOR classification. So this is giving you a geometric perspective. Okay, so the geometric perspective. So any type of classes are there, any type of classes, if their geometric perception shows if you plot those points geometrically and a single line can separate them, then you can use this. But if it is not able to separate, then this won't work. So now what happens, they were telling that the convergence of the perceptron is only guaranteed if two classes are linearly separable. And if the two classes can't be separated by a linear decision boundary, we set a maximum number of passes over the training data set, which is the training data set. All the inputs here are training data set. And a threshold for number of tolerated misclassifications. So that means what? Now here, what you can do is you can update the weights. When will you update the weights? When there is an error. So when you are, as Dr. Naresh was saying in his previous talk, there is prediction. What is classification? It's a prediction that which class it falls. Regression is also a prediction of the number, say the stock price. You are predicting the weather forecast. So it is basically predicting. And if I am trying to predict whether this particular student will get A grade, B grade, C grade, though it is a classification A, B, C, but it is also predicting. So this prediction, if you are seeing there is an error, then I can adjust the weights so that in the next pass, this error is minimized. Very simple concept. Okay. So in this particular thing, first of all, we have to check what error. So if there is an error, so what is there will be some error function, or it's also sometimes called cost function. What cost you are giving here means what error it is. So it is one of the error function is sum squared error. It is computed over all the input output pairs in the training set. So your training set will have multiple pairs of input output. So for example, it has classified the first student correctly. It has classified the second student correctly. Like that, out of 50, it has classified 45 students correctly with their grade, but 5 of them are wrongly predicted, so classified. So that's what it is saying. Overall, that 50 training set, it will compute for all of them, and then it will give the error. So now if there is an error, the weights will be updated. So when you are updating the weights, then there is one learning rate. So here you are seeing what is the perceptron output is. Here X is input, here X is input. Okay, perceptron output is D, Y is the actual output which should be there. So if you see, the perceptron output is actually the machine learning output and Y is the desired output. If both are same, then this whole second component in the addition becomes 0 and there is no need of changing the weights. So weights can remain the same. In case there is an error, say it's an error, then it will adjust the weights by reducing or adding. So there are many types of artificial neural networks. Feed forward. So this is what is the hidden layer, which actually helps in adding non-linearity in the learning. Before that, if you remember, there was one winter, AI winter, where it was saying that we couldn't solve it because there was only input layer and output layer. But here, once you see, this is the input layer, this is the output layer, that's it. But now they could solve it by using neural networks where we have a hidden layer. So the first type of the simple in artificial neural network was the feed forward, where all the arrows are going from left to right, only one direction. Okay. But there is an inherent interaction backward also, not in the arrows you can see, that is only the back propagation of errors. So what happens here is when you are getting an error, it back propagates telling which particular neuron did mistake, and accordingly that neuron connected with the previous layer's neurons weights gets adjusted. So the data passing is feed forward, whereas the error propagation is backward. So the error propagation, backward error propagation of error is responsible for updating the weights. So the multi-layer perceptron, if you see, it's used in pattern recognition. So let's see the perceptron structure. As I told you, the initial perceptron structure, when it was only one layer, inputs are there, output is there. So what happens is you have only linear separability, only one plane which is able to separate it, then it's okay. But if you see the non-linearity in this particular column where ABBA is representing XOR problem, the one layer architecture of perceptron structure couldn't solve it. Then the meshed classes are there, that is also not solvable. So now after the AI winter, they came to know we can use hidden layers. So the hidden layer was used. So this is 2-layer architecture. Now you are able to add the add the 2 lines to separate out the B. Now you are able to do it. So now in the meshed classes, if you see, it's having a curvature. So it's very difficult to put this properly, because if you see, some of the B classes is falling into A, some of the A is falling into the B also. Coming to the 3-layer architecture, now you are able to see that the representation of the data you are able to do more accurately. So what actually here we are doing is, the process is, whatever inputs you are giving, am I able to represent them properly? If I am able to represent the inputs properly, then it is very easy for me to classify them or predict their classes. So as we are adding more and more layers to it, we are actually trying to achieve a complex representation of the input. So what happens in your programming when you do not have any known architecture for a particular given problem statement? You try to experiment. So when you have tried with 2-layer architecture, then you will check the accuracy or the error. If you are seeing it's a huge error, then you can add more layers to reduce the error. So that means if you are adding more layer, what is your expectation? That you are trying to capture more and more intricate information from the given input. So what is that intricate information? Nothing but pattern. So you're trying to capture that pattern. So this is diagrammatically representing when we add more and more layers, the true representation is seen here. Some case study, if you see, it's from one of the papers here, 2016. They are able to use the artificial neural network in renewable energy resources in the energy market. It's basically, and here they are able to do the photovoltaic forecasting. Here they have some 20 neurons in the hidden layer, and it's having one hidden layer. What are the inputs? Inputs are output data, temperature, humidity, wind speed, some values are there. Okay. So here these are some of the values, the feature set, and this whole thing is trained for every set of input and output. This is not going for only once. So there are certain forecasts. So if you are having 50 places, 50 data, then 50 times it has to, it will go through for each set of input and output. Case study, if you see in environment sciences, they have used this in 2016 paper, where if you give the latitude, longitude, depth, the soil type, fault mechanism, here they have used 2 hidden layers. Then the magnitude of the earthquake classification, 4 classes are there, and they have used the multi-layer perceptron neural network consisting of the input, hidden and output layers to predict the magnitude of earthquakes. So multi-layer perceptron, nothing but artificial neural network, where you are having some 1 or 2 hidden layers. Here we are able to show to you. Now these are all feed forward. Okay. Now there can be feedback neural networks as well. I'm just giving you an idea, like there are different type of neural networks. So feedback neural networks are also called recurrent interactive neural networks, where the signals pass in both the directions. Not only forward, it can also go to back also. So when it joins backward, it introduces a loop. And once you introduce a loop, that means a memory concept. The concept of memory can be perceived in remembering. So when you have, as a human being, am I able to remember? Yes, I'm able to remember. How do I do that? I'm trying to connect to certain year back and trying to recollect what happened, and then again I try to connect to another event related to it. So I am going back and back. So that is what is the loop, recurrent neural network. So here usually we use, there are some Hopfield coherence self-organization maps. These have associative memory to store the pattern. So you have heard about dementia, correct? In dementia, people don't remember the old things. They just remember the present tasks, but they forget that. So what happens? The concept where the packet we are storing, that storage is lost. So this storage part can again see here we are telling that every decade we are advancing and trying to meet certain challenges which we have not solved previously. So previously it was only linear, we were not able to do non-linear. In 70s we are now able to do the non-linear, but now we are having a memory constraint, like can I remember, can I store some data? So feedback neural networks came into picture. So like this. So now there is a small quiz. You can write it in the chat box. Can we perform classification task using McLaughlin-Pitts model? Why Rosenblatt's perceptron failed? And how to learn nonlinear functions? Anyone would like to try? You can write 1, 2, and 3 and answer. I'll show you the evolution if you you can get some hint here. So McLaughlin-Pitts, the McLaughlin-Pitts is the 1940. Then what did I ask? Rosenblatt's, what was the limitation Rosenblatt's? What was the limitation of Rosenblatt's? And what did I ask? Second question answer anyone can give? What is the limitation of Rosenblatt's because of which there was a AI winter? You can see it in the picture also. Yes, only input output layers are present, correct. But what was the limitation? Gaurav, correct? No. Yes, it cannot classify. Then next is only input output layer are present, but what is the limit? Yes, the limitation was the non-linear. Rajaram Reddy, correct. Only linear problem. Now, how do you basically introduce the non-linearity? The third question. How do you basically introduce the non-linearity? Again, there is a picture which will help you in hints. Yes, multi-layer perceptron, multi-layers. So which layer you are using? Multiple output layers or input layers? No, they are called what? They are called hidden layers, Gaurav. Very good. Thanks for your participation. So let's move on to the next one. So yes, not possible because McLaughlin-Pitts model does not have any learning algorithm. I didn't put that diagram in that particularly the weights are fixed +1 -1, nothing we can do. When we came to the Rosenblatt's perceptron, it is learnable weights. So perceptron is the linear one, could not train the XOR function, which is non-linear. Actually, they got stuck with that XOR. So the XOR problem is also well known in literature. We say it as a non-linear. Additional layers provide the network with the ability to learn nonlinear functions. Okay, so thank you everyone. So now, where was I? Okay, so now coming to deep neural, this is just the evolution history. Deep learning, specified subfield of machine learning, where learning the representations from the data is the emphasis. So the feature learning, you remember these features were given, latitude, longitude, depth. Okay, this feature was given, temperature, humidity. Now, how I will know whether I have to choose temperature, humidity, wind speed? Why not any other measure? I just don't know what measures should be taken. That also, like if I want to say the magnitude of earthquake, why only soil type? Why can't we have some other things which will represent the earth better so that the earthquake magnitudes can be classified properly? So the environment science people, we have to be dependent on the environment science domain expert to give us the features. So now the new concept has come in the millennium, that can't we learn the features which are required to represent the data properly? Can it not be done automatically? That thing came into the mind. See, when we were kid, when we were told that, see, this is a dog, when your father showed an animal, was while walking with him, he showed an animal and told dog. Did he tell you, see, there are two ears, those are long ears, two eyes, black in color, the mouth is having one black spot? Was he giving you features? No, he was not giving features. He just told this is dog. And now your brain started to learn the important features automatically, seeing that animal. He never told you these are the features you should memorize. So there, this part was not tackled before this deep learning network was there. Every time we were giving some inputs. That learning of representation was not very automatic. Okay. So now if you see the definition here, we are telling that emphasis on learning successive layers of increasing meaningful representation. The deep in deep learning isn't a reference to any kind of deeper understanding. Rather, it stands for an idea of successive layers of representations. How many layers contribute to the model of the data is called the depth of the model. Layered representations via models called neural networks are stacked on top of each other. Okay, so here the purpose of layers, why we have the layers. Different layers will perform different transformations. Every layer is having some input. I'm not talking about the main input layer. I'm talking about the input from the previous layer. The previous layer can be input, previous layer can be another hidden layer. And it is giving an, after some transformation, because every neuron is actually a perceptron. It's actually having, it is collecting the connection from all the previous inputs which are connected to that neuron with a certain weights. Okay. And then it performs some transformation, some activation functions are given, and then it gives output accordingly. Okay. So now convolution layer is also there, which we will see later, that are doing with image data. So if you have an image data is actually looks like it is x m into n, correct? But when we are giving one dimensional data, then you can give all the data in the one layer. But if you have to give m into n data, then how you will use it? That time you use the convolution layer. So that time the image data, if you come across CNN, convolution neural network, it's usually used with the image data. Then there are recurrent layers that work with time series data. Then there are fully connected layers which connects each input to each output within its layer. So you will see there are so many types of layers. So when you see an already example architecture in some literature, then they will not say it's all hidden layers. I know they are all hidden layers, but some of them are convolution layers, some of them are fully connected layers or dense layers, some of them are used for recurrent layers. So there are many types of layer which you have to know. As the model learns, the weights of all connections are updated and optimized so that the input data maps to the correct output prediction class. This last line remains the same from 1940s. That means weights are updated. And why weights are updated? Because there was some error. If there is no error, then whatever initial random weight you have given, that works. But that magic doesn't work. If you are putting some random weight, it usually never works. After putting some random weights to all the connections, you check the error, how far it is from the actual one. and then you start updating the weight. So this part is always remains same. Okay, so for example, there is one handwritten digits. If Gaurav writes 9, Rajarama Reddy writes 9, I write 9, Shweta ma'am writes 9, everyone's 9 looks different. So it's handwritten digit. So can my machine predict that it is 9 properly? So this is one of the example where you have used neural networks. That is the hidden neurons are there. So input layer, if you see, it is here 1 to 784. What is 784? There was actually a image, this 9, when you have written, it was captured into 28 into 28. Okay, then you have not given it as an image. You did what? Every pixel you have given, say topmost corner to bottom right, bottommost right corner, every pixel you have actually flattened, and you have made it a vertical. So it is 1 to 784. What is 784? 28 into 28 pixel. What is 1? The first point. Okay. But if I would have given a spatial, the image, the spatial, spatial concept, then it would have been image. This is not an image. The inputs are 1 to 784. In the hidden layers, you are having 16 hidden neurons. And output, how many digits are there? 0 to 9, 10 digits. So somehow we have to have output 10 digits. In that example of magnitude of earthquake, how many digit output were there? 4 classes were there. So it was 4 output. So if you always see the output layer in classification or prediction, then if it is a classification problem, the number of classes are the number of neurons in the outermost layer. As simple as that. Okay. So what is ANN? CNN diagrammatically. You all now, all of us know hidden layer. This is the 3-layer output. Now in the CNN, what happens? This is becoming an image. This is becoming an image. And then you do some transformation. This is again a volume. How to decide? One second. How to decide number of neurons of hidden layers? Yes, it's a $1 million question, Rajarama Reddy, because not many people know. They are actually experimenting. So most of the time what we do is, if you know the problem and if someone has solved it, then why not use that architecture? Why to reinvent the wheel? But when he solved it, he has done trial basis. This is usually experimental basis. We decide the number of hidden layers and the number of neurons. Yesterday, if you remember, I have told you that there is a variance error, bias error. So variance error and bias error, if you see the error, if the error is having lot of variance error, then how you should operate, whether you should add layers or whether you should reduce the neurons. If there are bias errors, then you should add the layers or you should reduce. So it all depends. First of all, the weights which are put are random in nature. Initial weights are all random in nature. And then at very first iteration, you cannot come to a conclusion that whether your model is working fine or not. So they are called epochs. So you run it again and again, and till you are seeing that the error is minimized. And now you say that this is working fine. But now if you see, it took 3 days. It took 3 days to freeze the weights to a certain thing. That means it is not a good model. So what do? You want to learn quickly. So there are some hyperparameters like the weights, learning rate, and there are certain options in optimizer. All of these are there which you can tune up to learn fast also. So sometimes it is if you reduce the number of neurons or add certain layers, then maybe it is good. So it's all hit and it's a trial basis. Okay. So if you see in the CNN, then you will see this is volume of neurons. And finally, you have to flatten. Why? If in the first layer, see, this MNIST digit classification problem, you will tell, madam, can we use ANN or whether we should use CNN? I can say both you can use. If you are using ANN, then what you will do, from 1 to 784 in the pink layer, the circles you will put. And if it is CNN, you directly put my 9 image. It can put Gaurav's 9 image. It can put Ganga's 9 image. As an image you can give. So you can solve the same problem by using ANN or CNN. We'll see why we have to go for CNN for images. So why not ANN for images? Regular neural networks don't scale well to full images. So if you are having images, bigger images, then you will initially have 3072 weights. The number of trainable parameters are big when you are taking artificial neural network. And also one more thing is there. What happens if you are taking an image, you can see how the spatial the pixel, neighboring pixels are related, which is lost when you are putting it as a vertical, column vector. Okay, that time that you are just putting 1 1 1 2 1 3 2 1 2 2 2 3 3 1 3 2 3 3 like that. So when 2 1 and 2 2 were neighboring, how they looked, what was their connection, that is lost in this artificial neural network. But that spatial relationships between the neighboring pixel is retained when you are using the image. So obviously it will be more, it will be easier to use the convolution neural network to represent the input, and your feature learning, which we are talking about, automatic feature learning, will be very efficient. So this is what now, if you see here, see, this is the deep neural network. Deep neural network, as I told you, there will be many layers. Okay, so this is the input. Then it is an image. Okay, if it is a colored image, there will be 3 channels, RGB. If it is if you have converted to some other color space, you can have CMYK, then 4 also. It depends actually, whatever color space you have used. And now you will have some convolution layer with an activation function. Once you use this convolution layer, then what happens is you are not taking all the inputs at a time. You are processing section by section of the image. Section by section of the image. Who decides that? What is the section? How big is the section? That is being taken care by the filters used in the convolution. Whether this small box will be a 3 by 3, 5 by 5. So it depends how small area you want to study or how big area of the image you want to study. Okay, so here you are able to appreciate that the spatial relationship between the pixels are taken care very nicely. If you would have converted this whole image to a column vector from 1 to m into n, the spatial relationship would have been lost. So this convolution is very useful in studying the patterns in the image. So now what happens? Pooling, a very important concept, pooling. What happens when you have done, see here the car, when you have done a convolution, a small area you are studying, small area. If you would have studied here small area, nothing is there, background, it's white, no information is there. Do I want to capture this no information where you are having 0 values further in the neural network? No. So I want only the relevant data to be passed forward. So if you see the car portion, only that should be passed forward. So car portion, if you see, only a small area is there. So that's why you have a pooling layer which removes the unwanted part of the image, which it thinks that it is not a very important feature representation, and it thinks, okay, this is important, the wheels are important, so that only I should carry forward. So now you will see there is a convolution ReLU pooling, convolution ReLU pooling, convolution ReLU pooling. So in fact, there are so many layers of convolution ReLU. As I told you that if you add on the hidden layers, more and more representation of the accurate representation of the image you will get. Again, you will ask me question, then how many hidden layers I should have? I also don't know. I also don't know. So if depends on your image, say if you have a black and white sketch of an apple, and if you have the apple in a tree, if you have an apple in a tree in a garden, so you are able to understand how slowly that image getting complicated and complicated. So the garden, in that you want to focus on apple. So obviously you should have lot of more hidden layers to understand which is foreground, which is background. But if you are having a black and white sketch of a apple in a black and white without any background, only the foreground, then within 1 or 2 layers you will be able to understand. So if you're having lots of information and it's taking time to understand which is the foreground, which is the background, what I have to learn, then you need more and more layers. Okay. So there is a feature learning, and then there is a classification. So you remember two things are there. Feature learning is the automatic feature learning. As I told you, when your father showed you that animal dog, he didn't tell you learn 2 features, 2 years. This is the how much centimeter. See, now the cow is coming. Now see years, it's dropped. Years. How much is the centimeter? Never he told you all those features. Okay. So this feature learning was automatically happening in your brain. We are trying to mimic that learning here. So this is feature learning. Once the features are learned, then it becomes simple as an artificial neural network, where you are having passing on the features, and now you are doing the classification. This part is similar to the artificial neural network. So now you are flattening. So see here, this cuboid has been flattened to the column vector, and then you connect to each of these a fully connected or dense layer, and then you use the output layer to, how many here for the digits? You will have 10. If you are trying to learn car, truck, van, bicycle, 4 categories, then you will have 4 neurons in the output layer. So this is just a schematic diagram. 2 tasks are always done with the deep learning, feature learning, and the task itself. Okay. It is not always classification. It can be any other things later on. It can be segmentation, it can be regression, anything. But you should have good features to represent the your problem statement input. CNN is similar to the neural networks made up of neurons with learnable weights and biases. So performs dot product and optionally follows it with non-linearity. Input is transformed through a series of hidden layers. Whole network, why the layer has to be fully connected. So now what happens? Say for example, you have all the features, okay? All the features here. And now if you do not connect, if you connect, then you will understand which neuron is actually getting, say for example, the first neuron in this fully connected one gets connected with all the previous flattened one with high weights. Okay, so this become fired. Next one also fired. This one also fired. Next one also fired. So now if you have written one, if you have written one digit one, then certain pattern of the one will be fired and the rest will become zero. So if we do not connect each and every feature to the subsequent layer, then you may miss out that certain features you have not used at all. So you should connect each of the neuron with the next layers, each neuron, to know which is important by by first of all it will know that which particular pattern it is able to extract. If you don't give all the information, say for example, you have taken a printout of 3 digit 3, the printer was not working properly, and you in the 3 the first curve was dark and the last curve was very low. Okay, so obviously you have to consider all the pixels in that printout, is it not? Then only you will be able to say which part of this 3 is getting fired, all others are 0. So though the printer, if it is not working properly, this 3 becomes only one curve of this. But if you have given it properly, the 3 all are dark pixels, then what happens? You will be able to, you are not losing any information. If the printer is not working and in the 3 the next curve didn't get print properly, so you are missing the information. So it has to be fully connected to get all the features initially in the system. Okay, I hope it is clear. Okay, thank you. So in the whole network still expresses a single last fully connected. So last fully connected is called the output layer and its classification represent the class course. So now what happens, we'll see this. Okay, this one I have already discussed, but I will tell you in a, this is just a summary in a paragraph. 3 convolution layer, pooling layer, fully connected layer. Okay, so in that this is the convnet architecture. Now you will say in this architecture, how many convolution has to be there, how many pooling has to be there, we don't know. So I will tell you there are many proven architectures, we can use them. Okay, so always never have to, we should not do reinventing of the wheel. If someone has already invented the wheel, why not use it and make our own vehicles? That is more important than every time making the wheel thing. You make a wheel, I make a wheel, it is of no use. Use the wheels and make a new vehicle. So compile the model. Once you have made the architecture, you have to compile the model. This is very, very important. When you are compiling the model, I told you learning. What is learning? You in the first test you didn't get good marks. So now you have to learn what is good marks, what is bad marks. 100 was the total marks. You got 50. So obviously you know the error, and now you have to, your brain has to update the weights for those topics in the chapter. So there was a loss. There was a loss of 50 marks. So similarly, in the when we come to our machine, there is a learning. So have I learned properly or not? Who will tell? The first thing is loss function. The loss will tell if there is any loss or not. If there is no loss, that means I got 100 out of 100. So in model.compile, one of the loss function you have to give. There are many loss functions which you can just name it, because how do you compute the loss? Simplest is desired minus the actual which I have got. But there are certain loss functions, many types, which I'm not discussing here in detail. That name you have to give. Now comes the optimizer. What is optimizer? After you, this loss is then you have to optimize the weights. Why I am talking about optimizing the weights? What it has to do with the loss? Optimizer always has two objectives. Either it maximizes or minimizes. Can you tell what it will do with the loss? Which one it will do with the loss? What is the objective of the optimizer here with the loss? Minimize. Excellent. So Rajaram Reddy has told it will minimize. So the optimization, again, how in the optimization itself is a huge subject. So there are so many optimization techniques. Now there are differential evolution optimization techniques, stochastic gradient optimization technique. There's so many in the literature. If you find, still people are working on these optimization techniques. So some of them are state-of-art optimization technique already built in the software. So this optimizer name you will give. Okay, now comes metrics. As I told you, what is the metric? That how well your model is performing. Okay, always if you're not doing quantitatively, nothing is qualitative in this whole model. It has to be quantitative. Again, there are certain metrics. Yesterday in the session, I told you there are so many metrics. Okay, where so these metrics, again, remember, it depends on the class on the machine learning task. If you are having classification tasks, then the metric will be different. If you are having regression tasks, the metric will be different. Similarly, the loss optimizer, all these are related. Related means usually related on the tasks. Okay, so we have to do some learning on the state of art to find out this. Now once your model is ready, everything with the weights, now you have to train the model. Can you tell me what you need to train the model? Model is there, but what you need to train? Any guess? Weights I have already given here. Weights we are already having. Now we have to, yes, the weight values have to be, it will come, but weight values have to come before that. What it should have? When I say train the model, what is the thing which I have to give it to the model? Input, excellent. The data, excellent. Yes, you are correct. So we have to give the data. So I always tell, in machine learning, we have model. Whereas in programming languages, till now, before the machine learning, it was algorithm. In algorithm, you give input to the fixed algorithm, you get the output. But here, it is model. So there is a difference between model and algorithm. Okay. So model is having an algorithm, but it also needs the data plus the algorithm to, as you have told, the weights, to optimize the weights with the input given. And now it thinks that I am able to properly classify all the roses in the given collection of data. Okay, so if I am able to classify all the roses in the given collection of data, that means my model weights are trained to understand the pattern given in the input collection of roses. So that's why in machine learning, it's model, which the first few lines of the code, you have to write the model. Then you have to give proper inputs. Then only you will be trying to this. So here there is a fit generator which tries to fit the input to the model. When you say fit generator, it's trying to fit the data into the model. And then finally evaluate. When you evaluate, you get the score. Then you can use this. This is a simple step. Okay, now convolution, very quickly I will go through it. I'll just tell you the concept. Okay, not going to the mathematical explanation. This is the image. I told you in convolution, we will be studying a portion of the image. What is the portion, big or small, depends on the kernel. So what, something has come up. Optimize the weights, in some cases fit itself does evaluate, right? Yes, yes, yes. In machine learning, if we just write fit, it will evaluate. Correct, you're correct. This one in the convolution layer, the image you will be putting here, and you will slide it. And when you are sliding, whether you will overlap, not overlap, all those decisions can be taken. So the convolution applies kernels, which is this yellow into yellow, this part, okay, that traverse through the image and generate the feature map. So if you see it will be generating the feature map once it is brought. And how it is doing, a dot product operation takes place and the convolved feature is generated. If you see here, in this, these are the filters used. This convert feature, if masks are used, and you get the output: edge detection, sharpening, blurring, Gaussian. So these are all image processing. In image processing, convolution is a very, very important concept to get. You are trying to get some information from the image, whether it is or you're trying to process the image, you are trying to transform the image in such a manner so that you get the required pattern. So whether it is edges or whether you want to get some of the components, all of this. So this is the result of a convolution. So these convolution layers, if you see here, these convolution layer, if you are applying to certain image, then somewhere you are getting these responses and somewhere you are not getting any responses. Can you see this? Zero, no response here. In the first column, last row, nothing is there, no pattern is seen. Whereas somewhere it is being seen. Okay. So each of these 96 filters, so there are 96 filters given. So one image goes through 96 filters of size 11 into 11 into 3. And each and one is shared by 55 by 55 neurons in one depth. So these are some certain architecture already there in the literature. They are just showing, I have just copied from their paper, that how when you apply the CNN, then how this is being shown. So not all the filter is able to capture. So this particular filter was its output nothing able to capture. Some of them is able to capture. Can you tell in the first 3 rows what is so exciting about it? In the first 3 rows, what pattern it is trying to show? What it is trying to show? Edges, yes, correct, edges. But why the first 3 rows are very interesting? In that edge also, what is the thing which is interesting you? Okay, gray, one thing is gray, black and white thing is coming. What is the other thing? Very important information is getting captured. Yes, excellent. Direction of lines. Yes, Ganga Singh, you told correct. So what happens? Don't you think when it is handwritten digits will be there, this will really help us? It will really help us to capture where there are vertical lines, where there are horizontal lines, where there are curves. So like that. So now, which has created vertical line, that filter should be there in the bank of filter. If it is not there, maybe I won't have captured the vertical lines. So like that, they don't want to miss out any patterns hidden into the image. So they have given 96 filters for that. Okay. So, okay. So this is more about which I have told. Now kernels in deep learning network. Each kernel in a CNN learns a different characteristic of an image used for blurring, edging, and now there are stack of convolutions, the series of convolution. That means after one convolution with the activation function, I get certain response. Again, I give it to convolution. Again, I give it to convolution. So there are series of convolution which are they are used in deep learning networks, especially if I am talking about convolution, then we can tell CNN. Okay. Then there's a max pool layer. What happens in max pool layer? Non-highlighted elements are discarded from each feature map, leaving only the features of interest, reducing the number of learned parameters. What happens when you are having a small number of neurons? Then each neuron is connected to the other neuron with what? Each neuron gets connected to the other neuron using what? Can you type? One neuron getting connected to the another neuron. What is that? What is the information in between? Remember the diagram? One neuron getting connected to neuron on the edge. What did I write? Wait, excellent. Rajarami Reddy, excellent. So wait. So obviously if number of neurons are less, the weights will be less. If the number of neurons are more, weights will be more. Why? Every neuron is getting connected here or there and with a weight. So number of weights of the trainable parameters or hyperparameters will be more or less. So now unnecessarily, as I told you, if in my background of that car, it was all white, why I will carry the whole weights every time? The storage, complexity, everything will be there. So I will discard the non-highlighted elements from the feature map. How can I do it? By using max pool layer. Okay, this is a demo. So how I will know which is important? What I do is that whole image, always divide and conquer is the, when you have a big problem in your life also, what do we say? Take a day at a time. Relax, take a day at a time. So the whole being philosophical now, thinking what will happen after 5 months, whether COVID will be there, whether I just don't take day at a time. At least I know today what I have to do. So like that, when you want to know what are the highlighted feature, then what you do, divide and conquer, divide the image into certain. So now you can tell the one of the parameter as 2. I want to study 2 by 2. In the 2 by 2, which is the max? 20. Next 2 by 2, what is the max? 30. What is 2 by 2 max? 100. What is 2 by 2? 37. So I am now left with only these. So these responses have come. These are the output. These are the output of the activation function. And what did the activation function get? Activation function got all the summarized weights from all the neurons. Okay. And then it has got through the activation function. These activation functions can be linear, non-linear, simply telling greater than or less than, or maybe it is a sigmoid. You must have heard about ReLU, and there are so many. So I'm again not going into details about lots of activation function. It basically triggers with a particular value. Okay, so these values you will get, and now you do a max pool and see how the size has reduced. So non-highlighted features are discarded. So if I show you this this one here, see here pooling. You see here pooling, that whole cuboid now is a small cuboid. Then you do convolution, again pool a smaller cuboid till you are satisfied with the features it has achieved. That means these features are the highlighted ones. Then you flatten it and try to have the dense layers. Okay, so now that's what we have told here, pool layer. So this is what was 64. Now you pool, because you are doing by 2 by 2. So divided by 2, 112 into 64. So what is this 64? 64 filters. 64 in that example where I have shown you from one of the literature, this was how many filters? 96 filters. Now similarly you are having, see, this is filter. Okay, so here this is filter. So like that I am passing 96 of such. Say for example, if in this image I pass 1, 2, 3, 4, 5, 6, 7 filters. So I will get a similar picture in identity, edge detected. Then there will be another edge detector, Sobel's, Laplace, pre-weight. There are so many types of edge detectors. We are trying to use all edge detector. I don't know which one will capture what. Okay, then sharpen and all these things. After you have captured everything, it is still there in that layer. So now when it goes for a max pool, it still remains 64, no? Because each of that 224 by 224, once you have convolved and got 224 by 2, you max pool that. So you again max pool the another edge image, another edge image, sharpened image. So every filters you are just every filter response you are max pooling. So this number remains same, 64, 64. This is called also down sampling. Remember this word down sampling. If anyone asks like how do you down sample, finally this is the important information in the image I have down sampled. You remember thumbnail of a image. So in your when you want to get a thumbnail, how do you down sample, but you keep the image intact. Okay, so pooling layer down samples the volume spatially, also controls overfitting. This is very important. Yesterday I have discussed overfitting, underfitting. Okay, so unnecessarily I do not want to have noise neurons with their weights disturbing my feature representation. If I include the noise, then what happens? I am trying to overfit with those noise. Noise can be a real some feature only. It's not noise signal. I am saying which is irrelevant becomes a noise for me. You do not need a person's height and weight to know whether he is a intelligent or not. So unnecessarily I am taking height and weight and disturbing the whole distribution of the feature representation. So that becomes noise. Here noise doesn't mean like signal noise, I am trying to say. Okay, so that's why a pooling layer will always, so if you again if I say here 25 and 12 is noise, I am happy with the 37. If I have got 37 response, these becomes noise. In this particular, if I would have carried forward this whole thing, then 8 and 12 becomes noise. Similarly, if you downsample and noise is gone, means there you can control the overfitting. Then there is a ReLU operation, the activation function, where what you do is you just take the maximum value and pass it on. So the whatever is the maximum value obtained, that only you will pass it on. It is used for piecewise linear function. Okay, so here you cannot have a curve. Here in the curve you are just using the piecewise linear function, and in that whatever value you get, the maximum one you just pass it on. It's very simple that way. Now why you need layers? This is simply I have put it in my slides. Input layers, hidden layers, output layers, some notes I have made, so I have just put it. So you can go through this one. Input layers can be image or can be a sequence data. Then there are learnable parameters. You can learn it using convolution network, fully network, LSTM, I has told you, neural network. LSTM is another type of recurrent neural network. Okay, so these are the used for time series. So then there are activation layers. In the activation layers are there where it will perform the thresholding operation depending on the function. Then there is normalization layers, dropout. You know how to normalize a input. You have, you know, the normalization, data normalization. Similarly, if you have to normalize the data, you just have to have a normalization layer. You do not have to do programming as such. You just have to call and add that layer in your model. Okay. Then dropout layer. Why do you need dropout layer? Dropout layers are again, it helps in controlling the overfitting. You do not need so many parameters. You just reduce some of the neurons. So it will do automatically. You have to tell the percentage, how much from the model you want to drop out, 10%, 5% or like that. Then comes the pooling layer. Then the pooling layer also, here what did we do? We did max pooling. Okay, where is it? Here we did the max. If I want to do average pooling, then I will average the number and give it. So similarly, there are certain types of pooling layers, max pooling, average pooling, some more. Okay, now you will say which one is good. I also don't know, depends all on your problem statement. Okay, then combination layers are there. some more and more very specialized types of layers are also there. This is very important. Finally, you have to give output, and in the output, if you are having two classification, more than two classification, then how do you do? So as you know, the classification layer, you can have regression layer. What is softmax? I will show you with the diagram. It is easy for us to show this. So this one, left hand side, if you see, this sigmoid has been used as activation function, and the right hand side, softmax, has been used as an activation function. In left hand side, it is binary classification, class 1 and class 2, and right hand side there are multiple classification, class 1, class 2, class 3. So when you have the when you are using this binary classification, the loss function used is binary cross entropy. When you are using the multiple class classification, loss function is categorical cross entropy. Okay, so this is by rule. Okay, now can you tell me for MNIST digit classification, which activation function you will use? Which output layer you will be is applicable, left hand side or right hand side? Yes, the softmax. Because how many classes we have? How many classes? 10 classes. Yes. Naushad Gaurav, correct. So it is 10 classes. So you will use the softmax. So if you have seen anywhere any architecture, now you know that why it is there. Okay. And if you try to change and see what happens, maximum what you can do, you can change and see. So this is the sample code which I have taken from one of the references from the CoLab research Google. So what we are doing, it is sequential in nature. So a model will be told first, it is sequential. So that means there will be series of layers. Then there is a convolution layer. So here you will have to write conv 2D. You now know conv 2D, how many layers in that particular paper? 96 were there. In this, it is 32. And what is the size of the kernel? 3 by 3. What is the input shape? 28 by 28 into 1. So if I have written here 28 into 28 into 1, then it is not a colored image. Okay, if it is comma 3 means it is a colored image. So then you are normalizing. I told you, you can normalize the data. So see here, the model adds batch normalization. Then I told you after convolution, it has to pass through the activation function. Then only you will be able to capture the nonlinearity. Here you in bracket, you have to write which activation function you will use. Okay, if you see softmax is used at the last one. You do not use softmax here. Okay, you won't use softmax here. You will use ReLU. Then again convolution, what you will do? Convolution, normalize, activation, max pool. So now you know I want to downsample. I have found some features. Let me downsample and see which are the important features. Now again, I am not happy. I know this is a complicated one. To make the patterns get revealed, I need some more hidden layers. So again, you add, these are hidden layers. Okay, the convolution are nothing but hidden layers. Again, you add these layers of convolution, batch normal, ReLU. Again, you add a convolution layer for batch normalization, ReLU. Again, now you think, okay, now let's see what all we have got. So now you max pool again. See here, pool size 2 by 2. You can write 3 by 3. You can write 4 by, it depends on that. This is the place where you will be given the parameters. Okay. So now you have added the convolution layer. Now you are happy. I think, let me see. See, here happiness doesn't mean you are able to see quantitatively how the model is evaluated or performing. You think that it is enough. So now you flatten it. So after flattening it, what happens? 4 into 4 into 64 is converted to 1024, your length vector, that is the column vector. Okay, now what, as I told you, you have to have a fully connected node. Lastly, I have to connect all of these to the other. So how many you need neurons in that layer? It is 512. Again, the question is why it is 512, why it is no, why this sudden magical number? But that's how it is used. I myself have to find it out. Unless we experiment a lot, Nowadays it's happening like usually you have some state of art things and we use it, and then we also have to experiment, literally do some research and see what happens, and then you can write it. If it is 200, what happened? If it was 1000, what happened? Okay, so again, batch normalization, ReLU, you have to do this pakka large layer 5 of this. Then again you are doing what? To avoid this overfitting, what you did was dropout. Once you have done dropout, again you have to put it in the dense, okay, so that you connect it again to the, now the last layer, it has 10, it is MNIST one. You this one I have given, you can do it anytime, this code MNIST download and do it. Dense is 10 classes, so you have to put at the dense layer with 10 classes, which will be connected to the previous fully connected layer, to know which all neurons have fired. And you have to use softmax. What happens? The softmax gives you probability value. So if you are having probability value, say for the 0.96, 0.02. So 0.96 is what? The first neuron is 0.96, and that represents 1. So the output will be 1. Okay, so that's how the this softmax, what it does is, it's having a, this is actually a mathematical function which gives you the probability for each of the class. The highest one, you have to choose it as the output. Okay. Now convolution neural network architectures. This is what I have found. Like, you must have heard about these 1990s, they came up with LeNet, then AlexNet, ZFNet. See, now evaluation where it has taken from 1950s, from your McCall to now you are learning about so many architectures. Okay, Google Net. You know, there are world-class challenges in conferences, and if you are winner, then that you will give a name. Actually, they have given their name in that paper. AlexNet was there, Google Net was there, and if you are winner in those world-class challenges, then slowly what happens? This software, they adapt this architecture in their libraries, and you can directly use them for your purpose. Understood? So if they have told VGG net is these many layers, in each layer they are this many neurons, you do not have to add and do. You just have to call the VGG net function. That's it. And automatically that model will be stored in your memory. Like when you are executing your program in the memory, it will be stored. Okay, so that is what is the magic. When that's what we are saying, no need to reinvent the wheel. So already people are doing lot of work. You want to be one of those people, then you have to be a researcher, and I look forward to some of you to invent a new architecture, for there are so many open problems. Okay, so if you do, then your name or your model name will also be a part of the software library function. So this is what is the, this has come from ImageNet. ImageNet is the data set, large scale visual recognition challenge. There are 1000 objects, and it is able to identify 1000 categories. Can you imagine how much time it would have taken to train correctly all the 1000 classes? How many parameters it would have, and those parameters have been properly optimized to identify those 1000 categories. So now if you get those weights, wouldn't have been wonderful? Then you just have to use them. You just have to use them and tell me, see, this is my image in the scene understanding. I have taken this picture from my garden. Can you identify? Well, first of all, you have to detect which object you want to classify. You detect, so there will be one detection. Once you have detected this object, you put it in a box and give it to it, it will tell whether it is rose or whether it is a dog, whether it is an animal. There are so many objects like that. Okay, so this is where the magic is there. So all of these researchers, top class researchers, they actually did one thing. What did they do? Input was given, then there, as I told you, stack of convolution layers, convolution layer, ReLU, this whole thing into n. I don't know what is n. Again, you will tell me what is n. I also don't know what is n. They came out with so many numbers that there was so many 16, 14, so many layers, and then they are pooling it. So usually they do the pooling after 2 or 3 so that they downsample and then only they can go ahead. Then finally, once they have done this part m times, then they go for fully connected, as I told you, flatten it, fully connected dense layers, ReLU it. That also they do it for the K times. What is K? K is, can you guess what is K? What is K? I have shown this architecture. I know it is a bit difficult question, but can you guess what is K? No, 5 not, no. Lastly, we have come. Yes, it can be number of classes. Yes, Ganga, number of classes. So lastly, you have the fully connected. I think you are correct. Maybe it is some number. And finally, FC will come as a fully connected somewhere. Yes, this last one will be, I'm sorry, this will be the number of classes. Okay, after that, there will be number of classes. So this is what, if you open and summarize in the net, you will see this is nothing but this is a sequence where m, n, everything is a variable for them. So now I am introducing you a very important and a very popular concept, that is the transfer learning. It's a research problem in machine learning that focuses on storing knowledge gained while solving one problem and applying it to a different but related problem. Okay. Say, for example, ball. It identifies 10 types of ball. It identifies 30 types of monkey species. And now if you have given one monkey among them, it will identify which species also it is there. So it is a related problem. Okay, but maybe that particular monkey species, it has not trained, but it will try to find out the similar most species to that monkey problem. Okay, so the knowledge gained by learning to recognize the cars can also be applied to recognize the trucks. Okay, so you will have pre-trained networks. It is not easy to train 1000 category objects. It requires lot of time and computational power. So they have very high-end machines for training. So this training I won't be doing in transfer learning. I don't do any training. What I will do is, once I load that VGG net, then I will already get the ready-made bits. I just have to predict. That's it. And when you predict with a metric, it will tell you how much percentage it is accurate. So let us do the hands-on session with the deep learning using Keras. So now I am introducing the Keras. Last session I told you about the scikit-learn, where Ms. Upunika Burman Rai has also told you about the scikit-learn, regression, classification, libraries. Now we will talk about the Keras. Okay, that is also based on the Python open source neural network. It is capable on running on the TensorFlow, designed to enable fast experimentation with deep neural network. Okay, so let us study. I have uploaded in the Google Classroom IPython notebook file, which the thing is, it is actually convolution neural network, where I have told you the VGG16, how to load the pre-trained architecture of VGG16, which is trained on ImageNet dataset. And the objective is the pre-trained network inside the Keras is able to recognize 1000 different object categories, and we encounter in our day-to-day life. You can try to give any day-to-day life object and see whether it is able to identify the class or not. Okay. Shall I go ahead with the Python notebook as we have some less time? Is it okay? Okay. Any other questions? Then I will go. Okay, sure. Sure. Thank you. Thank you. So let me go here. See here in the Google Classroom itself, I have put this. Okay. The VGGNet. So today I am going to demonstrate actually the transfer learning. The other MNIST classification you can find anywhere. If you have understood the architecture, you can try it on your own. So let me see here. So let us see. So that's why I didn't give that one. I wanted to show you this one is very exciting. See here from Keras.applications. So if I plus code, if I say from the application, does it give? I was thinking it will give a dot. Okay, leave it. We will go this one only. What happened? Okay, so here we will run this one. So here there are many applications. VGG16. I thought if I say dot, it will come. Why it is not coming? Okay, very good. So applications. Now if I put dot, see here participants, you can see here all of these you can use. Inception, RESTnet, okay, MobileNet, RESTnet, VGG16, exception. These are already pre-trained models. Okay, that's what I wanted to show you. Out of that, we have used actually VGG16. Okay. So next time when you want to do any other things, then you just you can try any other of this. So import. So now what it has done is it has downloaded this VGG pre-trained model with all the weights. So now if I say, what is the model.summary? If I say, what is model.summary? It gives you the, see, this is what it is. Now you will be able to understand input layer. The input layer is a color or a grayscale. Can anyone tell seeing this? Excellent. So it is 3 layer. Okay, so it is input layer is a color one. Then what happens? There is a convolution max pool, convolution max pool. See, inside that convolution, when you are calling, that time, if you remember in that, I have told that ReLU has to be told which activation it has given. Okay, so that's a part. It is not a layer. It is actually after convolution, it goes through the ReLU. Then max pooling, convolution, max pooling, convolution, max pooling, convolution, flattened, dense, and the predictions. Okay. So similarly, you will find there will be all the architectures are actually having that formula I have given. Somewhere or other, m into n will be changing. So see here total parameters, how many it is training. It is having so many parameters to train. It has already trained also. Okay. Now the thing is, we will do one thing. We will here load image. We have imported a load image to array. We have another function, preprocess unit, decode predictions, import. Okay. So now, if I want to go, it will give error. Why ball.jpg is not there? Okay, so now yesterday I think Upunika has told you how to upload a file. I already have in my downloads a ball.jpg. Okay, so you download from it is saying what uploaded files will get deleted when this runtime is recycled, because in runtime whatever in memory you are having, that for that moment only it is uploading. Okay, now if I have used the ball, what it will do is ball image.array, here convert the image to numpy array, reshape the data for the model. Okay, so they reshape the data for the model and then pre-process the image input, and then it is directly predicting. It is not doing any training. Okay, so now let us see what error. Load image, no site. Oh, JPEG. The name is JPEG. So it is. So it is saying soccer ball, 99.92%. Let me see. I don't know whether you will be able to see here. Are you able to see the ball? Are you able to see the ball?
Yes, madam.
Yes. Okay. Okay. So here, where am I? So it is. They are saying this is soccer ball. So that means they have classifications of ball as well. Okay. So now you are able to see the magic. What is the magic here? Basically, the target size is 224, 224. Why? In VGGNet, the your input is 224, 224. Okay, so when I downloaded from the internet, that size, irrespective of whatever it is size, this will take 224, 224. Why? If you have seen here, see here, input size is 224, 224 into 3. So that's why when I am giving the input to the VGG model, when I'm giving the input to the VGG model, before that I use some image processing reshape function to give it to the 224, 224, and then model.predict. And once you have model.predict, then you are using the accuracy with 92. Now what is this? Similarly, you can use any, you just use any of these for your experiment. You download some of the images. I'm not going through this one. Monkey.image also same, this one, peacock.image. I just tried some bird, something. The code is safe. So you can use that. Okay, now there is another very important thing. Extract features from images. You remember I have told you in this whole CNN network, the first part was, and what was the second part given the input. What was the first part? Can you remember? The two very important concepts. The first part was what? And the second part was what? Why we are going with the deep learning? Why we are going with the deep learning? What is the thing which, as I told you, your father, son, father, daughters learn? Yes, excellent. So feature learning, feature extraction, correct. Learning the features. Remember that learning is okay. Learning is okay. Feature learning of it. So when you do not want them to tell, you do not want them to tell whether it is ball or not. Actually, I am having some, say for example, I'm just telling face recognition, and I know this particular model is able to extract nicely the patterns given in an image so that it can classify 1000 objects. So can it not capture the face features very well? Let me use these features and then apply for my classification. So what you will do is you can just extract the images from it. How you will do? See here. You will use the model now, VGG16, weights equal to ImageNet. What is ImageNet? If you remember, I don't know, I'm putting more pressure on your brain. You remember ImageNet? What was the ImageNet? What is ImageNet? ImageNet. Okay, I'll tell you. Nahi. BGG is the architecture. It's always good to reply a wrong thing. Then you know the correct one. POK क्या रहता है? Okay, अच्छा, okay. No. Acha, by the way, very good. This computation data set, excellent, Gaurav. So it is a data set. As I told you, model needs what? Model needs the algorithm plus data. Then only this model will come up with the trained thing after training. Okay, so here this is the data set which I am saying, the weights which have been used for training the ImageNet. Here we are using include top equal to false. By default it is true, because you do not, if you want to tell the classified classes also, then it will be true. Now because you just want the features, then you can just use the features. So this part will only give you the features. Okay, so here once you are using the load.image, then you can pre-process model.predict. This gives you features. I have to see whether it will. So it has downloaded, and elephant तो है नहीं यहाँ पे. Let me see wall. So no error came. So now this particular thing is actually the features. It is not predicting. We did not call any predict here. If you see the last class pre-process, then you are predicting. Okay, but here I am not predicting. This is nothing but I have mentioned here features. Okay, so this is what I will stop my lecture over here. So that's what you can see here. This whole PDF is what I have talked about in my presentation, and this is the transfer learning example where you can use the pre-trained architecture to classify directly, or the pre-trained architecture to get the features automatically, and then you use for classification or regression or for anything. Okay. Okay, thank you. And any other questions? I hope you understood some part of it.
Thank you, madam. There is one question from Smaran Rao.
Yes, correct. Using pre-trained model is transfer learning, correct. So I was talking about the transfer learning, and I have given a demo on transfer learning, Rajaram Reddy.
Madam.
Yes.
There is another question from Smaran Rao, sir. For VGG 16, is the image compressed to 224 by 224 pixels?
Yes,
size?
yes, yes,
or is
yes.
a section of the image of that size considered?
No. 224 by 224 is the input. Where are you seeing those questions? Here I am.
Question and answer section.
Acha, okay. There is another thing also. No. It is. It is 224 by 224 reshaped. I won't say compressed. It is reshaped to 224 by 224. Okay, the same question it has come. Okay. Anything else? Can we test pre-trained model using the pictures taken? Yes, I did that. That ball and everything I just downloaded from net only. You try your own images and see whether you are able to do. You take a picture of a cat or your dog or your pet dog and see whether it is able to tell the animal or not. You can test with your own image. Any other questions? Thank you. Thanks for your participation. It was very, I really liked this active, enthusiastic, active participants. It makes, because it's all online, so it makes easy for us also.
Yes.
Everyone participated very well. Thank you so much.
Yeah, excellent, Tilottama. I think it was very good talk.
Thank
Most
you,
of
sir.
the participants have asked questions.
Yes, yes, sir. Thank you so much.
There is
Can we go to the next part of the program, Shweta?
Yes, sir. Yes, sir. Thank you, Tilottama madam, for sharing your knowledge.
Thank you, ma'am.
So there is a token of appreciation from Hyderabad ACM chapter, madam.
Thank you so much, sir. Thank you, madam.
Okay.
Yeah. Thank you, Tilottama.
Thank you, sir.
Thank you, Tilottama ma'am. Kavita here.
Hello, Kavita ma'am. Thanks for giving me this opportunity.
Nice session, ma'am.
Thank you.
Sir, shall we ask participants to give the feedback, madam and sir? I request
We are taking the
participants
feedback.
to...
We just announced the closing of the program. What are the things that is going to happen under this? We are taking feedback from the participants. They can
No, sir.
speak up, one or two.
Yes, sir. Yes,
Then
sir.
we
One or
will
two.
formal vote of thanks we'll announce.
Yes,
And
sir.
then we will close the program.
Yes, sir.
Okay.
If any participant wants to talk, please raise your hand. We'll allow you to talk. Or put it in the chat box. Put a message in the chat box. We request one or two participants to speak about the 3 days workshop. How was your journey?
Yeah.
If you raise
Good.
your hand or else,
To our future programs too.
yes.
Naushad, please speak.
I have moved Naushad to panelist. Informative, cannot
Shweta,
please.
Naushad wants to speak.
Yes, sir. Yes, sir. I have moved to panelist.
You please unmute yourself and try to speak.
Yes, now you can speak.
Yesterday also it was the same problem.
Now you can unmute yourself. I have given co-host permission also. I think he not connected to audio. Please connect to some audio. Sorry, something wrong with my mic settings. Okay. So anyone else, please? All the sessions were excellent, very interesting. The best part is the live demo sessions with examples from Ganga Sanwala.
Thank you.
Thank you.
Thank you,
If
Ganga, for your comments.
anyone who wants to speak, I'll move you to panel list. Rajaram Reddy, sir? Oh, sir raised his hand, okay. Naneshwar Ramita. Just a second, sir.
Dr.Naresh sir, can we move ahead?
To speak, people want to speak, but seems like some issue is there. Okay, we will go ahead. We'll
I have
propose
added
the vote of thanks.
Naneshwara Nitta sir and Rajaram Reddy sir. Rajaram Reddy sir wants to speak. Sir, now you can speak, sir.
Okay.
Hello.
Yes, sir.
Yes, sir.
You are audible.
Yeah. So I've joined the last ACM Hyderabad chapter workshop as well, and this is the second one. So I'm finding these sessions very informative, and practical. So this time, some of the sessions were little, they've gone over the head for me, but I have gained some of the other knowledge. So I'm finding them interesting, and I want more of these workshops to continue in the future. So yeah, I'll be very happy if we can continue these workshops. Thanks a lot.
Thank you, sir.
Thank you, Mr. Rajaram Mohan.
From Naushad, it is sessions were good, a mix of basics and advanced topics. Okay, sir. So now we'll move to the next session, sir. Vote of thanks. I request Naresh sir to propose vote of thanks.
Shweta, give me an opportunity. Then Naresh sir will address the participants.
What,
Okay.
So I congratulate all the participants for successfully completing our 3-day international workshop on artificial neural networks, variants, theory and practice. I hope you all had knowledgeable sessions and you enjoyed, and I hope you are ready to dive deep into the domain. And we tried our best to give you best lectures from the people who are very specialized in the particular topics, and you had a very good experience with the hands-on sessions. And you have seen Dr. Tilottama and Uponika and Dat Tran. All these people have tried their best to give you hands-on experience so that you can quickly start and explore more on the topic. And I thank all the speakers for giving consent and taking their time and giving wonderful sessions. I thank Professor Akira Hiros, Professor Rammurthy, Professor Marley Velasco, Professor Tilottama, Professor Risto, Professor Alexandros, Mr. Dat Tran, Dr.Naresh, Ms. Uponika, everyone for their wonderful efforts and the great sessions. And I also thank the people who work behind the curtains, and I especially thank Ms. Sveta for sparing her valuable time in coordinating with the speakers and as well as participants. And I also thank Dr. Raghu for giving us, facilitating us with all the Zoom configurations and settings, and to see that the whole program goes as smooth as possible. And I also thank our other volunteers, Professor Sudha and Dr. Krishna Kirti, for helping us in smooth conduct of this program. Last but not the least, I also thank our student volunteers for supporting the event for all these 3 days. I thank Dr. Naresh for allowing us to conduct this international workshop, and he did a lot of background work in bringing this workshop into the proper shape. So I thank all the participants for adapting to the timings of the workshop and without any reluctance attending all the sessions and for their active participation. And now I'll request Dr. Naresh to address the participants. Thank you all.
Thank you, Dr. Kavita. I think you were always there in the organizing this particular workshop. You have been the backbone of the chapter, and I thank you and your team. In fact, when I envisaged this project, it came out very complex. Okay, because there are multiple zones, the speakers, and even the later we had few participants who were from across the time zones. So we had to restrict to 2 to 8 p.m. I understand that there were some difficulties, and always when a program is there, we encounter several situations being this COVID and heavy rainfall recently. But still, all the speakers were on time, and I should thank them for keeping up, the whatever agreements we had, and also the participants were really good. Though we had the numbers were fair enough, but everybody continued up to the time that we asked them to be there. Especially on the second day, we ended up to 10 p.m. But very interesting lecture from Professor Risto and even Alexandros. Every international participant like Akira Hirose has speakers have given excellent introduction to ANNs. I think this should form the basis if you are into research or if you are thinking further doing something. I think this is an excellent material that you are having now, and especially the Alexandros and Dr. Dat's, Mr. Dat's work, wherein the research is there, publication is there, and you have the code with you. So to verifiability is many research papers are that you get the paper, you don't have the data, you cannot write the algorithm, it's very complex. So no way to verify that particular paper. Now, I think that's wonderful work on COPS. And thanks to Tilottama, she has excellently put the deep learning part hands-on.
Thank you, sir.
Pony also for her wonderful participation in presentation. We have been inviting her for 2 programs. She was there for the hands-on session, and Sita and Dr. Kavita, Dr. Sudha, Krishna Kirti, Dr. Raghu. I think we have an excellent team. Only when we get into the program mode, everything works on well. I think I should congratulate the chapter, also participants, and thank the speakers. And don't forget, continue your work. Be in touch with us. We will be sending you our programs. We have created a WhatsApp group. We will also see how we can put up these videos and share with you. We'll come up definitely with some way of sharing videos. Okay. And be in touch with us, and see you soon for our next program to come. Thank you. Thank you all.
Thank you
Thank
all.
you, sir. Thank you, sir.
And I formally announce the closure of this program. Thank you.
Sir, participant certificates will be given by Thursday, sir. And I have shared a feedback form link. Please, participants, please fill that form. In the chat box, there is feedback form. Please fill that. Okay, sir. Thank you.
Yeah. So, with your permission, we can wind up this meeting. And if you have any queries, you can contact us on our phone numbers given in the WhatsApp or in the mail ID through which we have shared some of the information to you. Thank you.
Madam, shall I end the session?
Yeah, you can, Shweta. Thank you.
Thank you all.
Oh, speaker PPTs, that we have to take the permission from them. Once we consult them, we'll get back to you. If you have recorded sessions, that is good enough, I guess. Regarding PPTs, we need to ask them. Thank you. Dr. Naresh sir, can we end the meeting now?
Naresh sir is not there, madam. I am ending the meeting.
Okay, okay. Let us take a call then. Okay, thank you all. Good night.
Okay, sir. Definitely we'll share. You can subscribe to our YouTube channel to get all those recordings.